today will be just as enriching. We have an exciting lineup of speakers and topics ahead. So let's dive into another day of exploration, knowledge sharing, and collaboration. Thank you for being here, and let's make today as impactful as yesterday. Enjoy the sessions. It's my pleasure to introduce Dr. İsa Atipoğlu, a leading researcher in photonics and electronics. He earned his bachelor's degree from RGS University and later completed an MSc in electrical engineering at the University of Alabama at Birmingham, focusing two-dimensional real-time range imaging. He then pursued a second MSc and a PhD in optics and photonics from CREOL, University of Central Florida, with research on photodetectors and gallium oxide for UV detection. Currently a faculty member at Gazi University, Dr. Hatipoğlu will share his insights on integrated multi-wavelength lasers. Please join me in welcoming him.
Good morning, all. Today's topic is going to be on solar blind photodetectors and its applications. Before starting, I'd like to thank the organizing committee for their kind invitation and all of you that contributed to this very nice event. So I have put together a lot of things. I'll try to be as concise as possible. And for that reason, please, if you have any question through the presentation, please stop me and ask your question. Don't hesitate. So first, I'll provide some background information on deep UV detectors, solar blind detectors. Following that, I'll discuss why we picked gallium oxide as a material, detector material, and the inherent shortcomings of gallium oxide material as a photodetector. To address important limitations, I'll show you its drawbacks, and I'll present the focused work that I've worked for like past couple of years, maybe like 5 years, to resolve them. And after that, I'll show you 4 experimental work. Then we'll move on to the kind of results section, where I'll present the theory behind the experiments. Then we'll conclude. Hopefully, it's not gonna be that long. We'll see. So to begin with, if I move here, cannot, right? Okay. So solar blind, yeah, it's fine. So the ultraviolet region is divided into 4 subbands. While the most of UVA and a little bit of UVB light is reaching to the Earth's surface, UVC and extreme UV frequencies are absorbed by molecular oxygen in the atmosphere, and the leftover is completely blocked by the ozone layer. Therefore, the wavelength shorter than 280 nanometer, as you can see here, is called the solar blind region. So this area provides us with a background noise-free medium where we can, have a lot of different applications. So the main contributor to this blockage of UVC light is ozone layer. As you can see here, it has a Gaussian shape profile for its absorption, and it's centered around 255 nanometer. Then the molecular oxygen absorbs almost completely below 220 nanometer. For this, this is done for like 500 meter distance. So like for short distance, yes, you have some UV, propagation. However, for long distances, you will not have anything because of molecular oxygen. Then, of course, we have Rayleigh scattering, which scales 1 over lambda to the 4. So we have exponentially increasing Rayleigh scattering as we blue shift. So all things considered, you see a transmittance simulation, done it in Motran simulation. So here you can see the transmittance data for a kilometer, and below let's put it here, below 220, we have nothing left. So that's why I defined this range as a application window for deep UV detectors, for especially atmospheric applications. So many of you might think that, okay, UV is dangerous, right? We use it to kill bacteria, viruses. So how is it going to be useful? So there are certain limits that if we are below that, it can be utilized. And this limit is much lower than the, let's say, 400 nanometer light. It's almost like 100 times lower than the 400 nanometer light. So how is it going to be useful? How is it going to be used in applications? So for those applications that not like communication that we actively generate UV light, for others it's already there. So if we like it or not, there is lightning, there is missiles, there is fire. It's already there. So detecting that has no issue. However, for recently, I'll talk more about that. Recently, communication applications, these kind of like applications require you to generate UV light, deep UV light. For those, we have to be cautious. We shouldn't cross past the limits. However, for this, remember I said that there is a background noise-free environment. So since there is no signal in UV range, in solar blind range, so we don't need to have high intensity light because there is nothing there. So for instance, for IR imaging, the sunlight, the black body radiation is a big noise contributor. However, in UV, there is nothing. So we don't need high intensity light to do communication. A little bit of light is enough. So we will have high signal to noise ratios, and we can detect very, very weak signals. So for these reasons, there are several applications drive the need for solar blind detection. One of them is flame and missile detection. Solar blind region is especially useful for like the defense applications. You can see a flame's emission spectra here, and as we go to the solar blind region, there is nothing in the background, but there is a signature of flame or a missile that is burning some gases, some whatever it's burning. So the other application is non-line of sight communication. Remember I said the Rayleigh scattering is really high compared to like visible light and much higher than IR. So this drawback can be an advantage. So we can use it as like non-line of sight communication. For instance, for like optical communication invisible, we have to shoot laser and we have to target the laser beam with a detector so that we can start the communication channel. However, here, when I shoot a laser, let's say we have a laser in the UVC, when I shoot a laser, it's gonna be like a shotgun. It's gonna go like it's not gonna be directional. So some people use this property of UV light for non-line of sight communication. Again, it's especially important in defense applications or like military applications. Lately, people are trying to use non-line of sight UVC communication for short distance communication channels. So there's also space-to-space communication. Since we have an ozone layer blocking the UVC passage, so if we utilize UVC for like inter-satellite communication, it's going to be a safe, secure channel because we cannot interfere from Earth's surface. And of course, monitoring ozone hole for environmental purposes, it can be utilized for that naturally. And UV light has been used for very different applications like lithography, and there are a lot of different like sanitation applications. So we know that yes, it is dangerous. So if we are utilizing that, we have to be cautious. So we have to inspect if there is any leakage. So for those, we definitely need UV photodetectors. And there are other applications like medical applications, gas sensing applications, etc. So before I move on, last thing I want to emphasize is underwater communication is being very popular recently. And if any of you are interested in UV communication, you see here, these are from this article. You can check it if you're interested. So the absorption coefficient of water is shown here, and you can see that the lowest absorption occurs around 350 nanometer, which is in UVA. So, however, there will be some background noise. So if you compare signal to noise ratio, sometimes it is much better to work in UVC because there is no background noise, and sometimes we can have higher signal to noise ratios. So that is opening up new doors for underwater communication. So before we go into the details, here are some basic photodetector parameters that I'll use throughout my presentation. So quantum efficiency represents the conversion power of optical input to electrical output. And we have reflection loss here, so we lose that. And we have transmission loss if it is not, if we put something like to reflect all the light and get back to the material, that's fine. But here we will have for sure a transmission loss. And these are, you can see 1 over r, 1 minus r, and 1 minus e to the alpha d. These are showing reflection and transmission losses. And this zeta term is the fraction of charge carriers contribute to the detector current. So that represents many things. Everything is lumped into that coefficient. So that is to say like dangling bombs. dangling surface bonds, like crystal defects, or like phonon losses. Everything is like, it's basically saying that you generated an electron hole pair and how much of those are going to contribute to the current. So generation doesn't necessarily say that you will collect all of them, right? So we will have some transmission transport losses. There is spectral responsivity, as the name suggests. It gives us the nature of the spectral response of the device, and we can experimentally measure that. Responsivity is related to quantum efficiency with this equation, and if there is any gain in the system, we can, assuming that external quantum efficiency is 1, we can find out what the gain is experimentally easily. So noise is another important metric for photodetectors. Noise equivalent power tells us what is the minimum detectable power in a detector. So as you may say that we cannot detect any signal below noise level, right? So for background limited photodetectors, which UVC detectors are, we can estimate that with this equation easily. And the next important figure of merit is detectivity, and it is 1/NEP. And if we normalize that with area of the active area of the detector and the bandwidth of the detector, so then we'll have specific detectivity. If we use specific detectivity, now we can compare different detectors with different active areas and different bandwidths. So the temporal characteristics are also very important because that limits its use in applications. If it is fast, yes, we can use it for communication, but if it is slow, we cannot. Or like, for instance, flame detection, yeah, we can live with seconds of rise time, fall time. But for certain applications, if we are going to make a UV camera, 3-second rise time, fall time is going to kill everything, right? So it is very important. So all these parameters are intrinsic to the material. Some of them, like a band gap, right? Some of them are very dependent on not only the material, but also how it's grown. Because growth mechanism will change many things. Like you can grow the same material with different growth techniques, with different growth parameters. They are going to be different beasts. So we have to be cautious for that. While some properties can be tuned by device structure and fabrication, most crucial parameters, such as response time and spectral responsivity, can be manipulated by growth, which is my primary goal here. Here, this is, I have to say this, I want to be quick, but some people think that, okay, if they're going to make a best photodetector in the world, like what is the mindset? What should we do? So if we find the perfect grower and make a perfect crystal, and if we find a perfect team for fabrication and put them together, we'll have the best device. No, that's not going to work, because the functional photodetector, functional devices will not give you that. Maybe yes, you will have like having the best crystal, you will have maybe like faster, transport, etc. But eventually the functional properties are going to be much more complex than that. So that's why we have a we need to have a comprehensive understanding of growth, the interplay between growth, fabrication, and the physical phenomena that's happening. So that's why the research scheme, most of this work, and some of them are after my PhD, but most of them are from my PhD work. So we have a plasma-assisted molecular beam epitaxy here. So as you can see, everything is centered around material growth. Why? We now know. The design, fabrication, material growth, these are, we need to be careful about like what's the effect of one to other, etc. That's why we need a rigorous characterization, like structural, optical, compositional, and device characterization. And that is not enough. Just to reporting these characterizations will not give us anything. Okay, I've done this. This is the result. But why? That's the beauty. So why? It's a very nice question, but answering is sometimes very painful. So for that, again, we need to have a comprehensive understanding, like what's going on, what affect what. So having said that, I hope I was able to give you a nice introduction. At this point, is there any questions? Okay, perfect. Next, I'll briefly present the state of the art of gallium oxide photodetectors in view of material properties. But first, of course, there have been many other materials. People worked on them, and there were some shortcomings that those research to stop. Maybe they'll find some ways to, to move on. Algan, for instance, one of them, but it suffered high dislocation densities and point defects. Like ternary alloys like magnesium zinc oxide and others suffers from like complex alloying mechanisms and phase segregation. One, for instance, like magnesium zinc oxide. So magnesium oxide is like very ultra wide bandgap material. You alloy it with zinc oxide to tune the bandgap. As you put zinc oxide, okay, you start shrinking the bandgap, shrinking it. At some point, there is a phase segregation. Whoop. You just lose some spectrum that you cannot cover with detector. So that was, for instance, the biggest issue for magnesium zinc oxide. There is, of course, diamond. Diamond is diamond, but it's expensive and we cannot tune the properties easily. So that's why gallium oxide is a natural ultra-wide bandgap. I'm sorry, ultra-wide bandgap material with 5 polymorphs. Only monoclinic phase is stable. And throughout my presentation, when I say gallium oxide, I'm talking about beta phase gallium oxide. So that's why, like initially, gallium oxide got huge interest mainly because of the availability of low-cost native substrates like edge-fed film growth mechanism provided us with lower-cost gallium oxide substrates. And then it has become a natural choice for deep UV detectors for several reasons. One of them is its optical bandgap is in the application window I showed in the beginning of the slides. So the other good properties of gallium oxide, it has a nice n-type dopability and high radiation hardness and chemical resistance. So it also has like very high breakdown voltage, like maybe 3 times higher than gallium nitride. That's why people are like the power people are working on gallium oxide a lot to have smaller, better performing power devices. maybe we will see in the future, like you've seen the gallium oxide adapters, right? They're like this much tiny, and the performance is amazing. So maybe gallium oxide is going to be the next candidate for that. Theoretically and experimentally, it is showing a good promise. So, okay, gallium oxide is perfect. Then, like, why are we doing the research, right? So there are, of course, a lot of issues. So one of them is there is no p-type doping. I mean, there is, but it's not viable. So people, including me, I worked almost a year without any result. So like many days, many nights with like magnesium doping and everything, nothing. Sometimes you have no result, but on the way, it teaches you research is paid. So not many options with PN junctions. Therefore, what's the solution? We can use Schottky junctions. Why? Because we need, for an N-type material, which we have with gallium oxide, we put a metal, like high work function metal. Therefore, we have a mechanism to separate charges. Perfect. So there are, of course, some issues that we cannot address because they are intrinsic to the material characteristic. So the poor hole mobility is the biggest issue with gallium oxide. If we are gonna, abandon gallium oxide, this is gonna be the one reason why. Poor thermal conductivity is another issue. But these are okay for Schottky barriers because in Schottky junctions, we don't need like huge active areas. The distance is short, and we collect holes in some clever way that it's gonna be okay. So the focus shortcomings are reducing the cost. How? We can do heteroepitaxies with silicon substrate or like sapphire substrate or some other cheap substrates, right? And there is, as you remember, the band gap is in the middle of the application window. So that means we probably will not be able to cover the whole spectrum with photodetectors. What can we do? We can do band gap engineering, straightforward. Indium oxide and tin oxide would be a good choices for these. And there were and there still is a lack of understanding with impact of growth conditions on functional devices. So what we can do this rigorous analysis to systematically try to understand the physical phenomena behind the device properties. So I have 4 experimental work to show. There will be, I have to be a little bit quick. It's been 40 minutes. So please, if you have any questions, stop me. Otherwise, I'll be fast. So here, the first shortcoming, reducing the cost. So to reduce the cost, we can use heteroepitaxies with a cheap substrate. If we can grow gallium oxide on it, and at least like polycrystalline, because this is not going to be actual epitaxy, right? Because the silicon and gallium oxide has different crystal size. The lattice will not match. So my focus here is to achieve at least polycrystalline gallium oxide and have functional devices. So if the device is working perfectly, no one cares if it's polycrystalline or if it is, single crystal. So for that, it has been really hard to even grow gallium oxide on silicon with plasma-assisted molecular beam epitaxy. So here, what I'm showing that if we directly start the growth. Gallium, oxygen is there, silicon is there. There are there are many people with like chemistry background, so I don't need to say this, but for younger audience, so when there is oxygen, silicon just grabs that. It doesn't let the gallium, to have it and form gallium oxide. So here you see XPS experiments, which are showing short story long, which are showing that with if we send directly gallium and oxygen together, it's not going to form gallium oxide. The growth is impossible. So how we solve this issue? We utilize the gallium predeposition at least for 10 minutes, which this graph is showing 5 minutes is not enough. Then we were able to achieve the gallium oxide growth. So this is the unsuccessful growth. You see that it's not growing thin films, it's growing like island shapes. And here, as we grow, so what's the role of oxygen flux? As we grow in metal-rich conditions, instead of forming beta gallium oxide, we are forming GaO, which is volatile, and it prevents gallium oxide thin film growth. So for that, we concluded that, okay, minimum of 2 SCCM is required for oxygen flux, and 2.5 SCCM is good to go with. And impact of oxygen flux here, you see that as we go higher oxygen fluxes, we started to see the polycrystalline phases of gallium oxide. So here, what I want to show is substrate temperature is also a very important parameter in MBE. So 730 degree shows us good polycrystalline phases, while the lower temperature is also showing that usually in MBE, lower temperature growth gives you poorer, at least, crystal quality. And I'll show you in a minute. That's why we use like 350 for optimum plasma power. So luminescence is, as you know, it's a good technique to find out how the crystal quality is, like, is there any defect, etc. So here, I don't want to go into detail, but I have to say a few words. Like, we can see that we have green band, red band, and UV band, blue band. So these are all signatures of the certain defects in material. So I'll talk more on the defects. So you see, once we achieved a nice thin film, the next thing is to fabrication. Here I'm showing the device structure. So what we do, we first do a lithography for platinum. This has to be very thin because the light is going to penetrate through it. So it's a 3 nanometer of platinum. It's a high work function material, and there has to be 2 functions. One, it's going to be transparent. The other one is it has to give us a nice Schottky junction with the gallium oxide layer. So then, second lithography, we put nickel gold for probing. It has to be, I mean, 3 nanometer platinum. If you put the probe, it's gonna just punch through, right? So we have to put something there. The other side, the titanium gold, titanium forms ohmic contact with silicon after annealing. For sure, first we have to do the back side and then do the other side. So here you see that in dark, the black is dark. So in dark, we have a nice rectifying behavior, meaning that we achieved a nice Schottky diode. But as we turn on the light, now we have a photodetector, right? In reverse bias, we see that, okay, we have a nice photo to current ratio. So here is the normalized responsivity, which is showing how the detector is functioning in spectrally. So here, please see that there is one bad detector. It is out of the range, and also it has high dark current, as you see. That is the sample grown at 660 and annual.
I would have done question.
Yeah.
Well, you said that gallium oxide is actually N-type.
Correct.
And it is almost impossible to make it P-type.
Correct.
So would it be possible to use a P-type silicon substrate instead of an N-type one?
Perfect. Perfect. So I've tried that a lot. So with PN junctions, because of the electronic band alignments, it doesn't give nice results. So there's trapping because of the conduction band and valence band discontinuities. The charge carriers trap in the interface. So it didn't produce good results. But with other P-type materials, if we can, grow, yes, because the crystal quality should be good. Like if we directly deposit, we will have high dark currents. Like for instance, like magnetron sputtering, I just put a P-type silicon or like some other material P-type and deposit it with like sputtering technique. That is gonna give me like these results, by the way, are one of the best results in the field of solar blind detectors. Like to achieve that, it is very important to have a good crystal quality, at least like. So moving on. So here, please see the C1 sample, which is grown low temperature sample, and it has highest responsivity. So remember, I said low temperature comes with bad crystal or like a lot of defects. So annealing that, what it does is we are improving the crystal quality, but we are losing the gain. So there is, don't forget this. So as we anneal it, you see this the bottom one is that belongs to the low temperature growth sample, and it is the slowest one. As we anneal it, the blue one here, that is getting like twice faster. It is twice faster, right? So what's happening is that this implies that, okay, we are reducing the defects in the crystal, and that is improving the temporal characteristics while it is hurting the gain. So take home message: responsivity is correlated to crystal defects. Trade-off between responsivity and response time is there, and we have achieved a cost-effective way, and the results were really good, like much better than like homoepitaxial results, etc. So this gives us the possibility for on-wafer integration with silicon photonics and electronics. I have to put it here because it's silicon. So moving on to indium gallium oxide. So now we achieved the cost-effective method. Now the thing is, we have to do two things at the same time. One, reducing the cost by using sapphire. The other one is tuning the wavelength or cutoff wavelength of the detector. So why, you may say, okay, on silicon, it was fine, right? Why are we alloying? So as we change the substrate, because of stress strain, the crystal, the gallium oxide layer, the thin film, will have a little bit of different properties. And usually what happens is the band gap is much higher than actual band gap. It's like 5.2 EV, around 5.2 EV. Therefore, on sapphire, if we are going to do this, we have to alloy it so that we can shrink the band gap, and we can use it as a UVC detector. So here I have 3 samples. This, by the way, this has done in MOCVD system. Sample A, the base sample. B is higher pressure. C is higher temperature. I mean, my focus is not to give you the growth parameters or anything. So that's why I'm going to be fast. So you can see that, okay, all the samples are polycrystalline, and we achieved the band gap engineering, and the results are here. You can see that these are a very nice profile. I mean, what are we looking for? The ideal case, it comes 0, 0 at 280, goes 1, right? That is the ideal case. And we are very, very close to that ideal. And again, we studied oxygen vacancies with XPS here. So you can see that oxygen vacancy, the amount of oxygen vacancy is correlated to the gain. Please don't forget this too. So the main takeaway is, as we increase indium composition in the films, so that resulted in higher oxygen vacancies and higher dark current, right? So higher defect density resulted in, again, higher responsivity. Higher defects, higher gain. So, but what's the drawback? The drawback is, yes, we have higher gain, but now we have slower devices because of like charge trapping, detrapping. So next, a new alloy, tin gallium oxide. So again, I started with the thing that we achieved, right? It was painful, so why are we not using that? Tin gallium oxide on silicon and with a buffer layer. So what's gonna be the effect? You see that, okay, with we achieved a polycrystalline tin gallium oxide, and so you see that, okay, just tin gallium oxide on silicon looks good in XRD profile, but we have nanovoids. So because of the nanovoids, when we fabricate the device, the functional properties are hurt because of that. So to eliminate that, we use a buffer layer to smoothen the surface morphology, where we have better metal semiconductor junction. So again, the same type of structure we used, and after fabrication, we have rigorous characterization. Like IVs, you can see we have nice rectifying behavior and very nice responsivity, like, or it's correlated, so photo to dark current ratio. And you see that it is much better than just gallium oxide. This slow one is gallium oxide, and faster one is tin gallium oxide. So now we improved the temporal characteristics too. So since we are thinking that, okay, it is correlated to the defects. So you see the CL spectra here, and this is gallium oxide, and the red and blue are tin gallium oxide with buffer and without buffer layer. So what I have to say here is that you see the hyperspectral cross-section images here. So you see the gallium oxide. This is gallium oxide buffer layer. This is gallium oxide buffer layer. The red and UV emission spectra from CL is mainly coming from in the form of UV and red light. But as we add tin oxide, as we alloy it with tin oxide, the emission spectra shifts to blue and green. So at the time I was doing this research, I was checking the literature. There are a lot of attributions. Okay, it can be that, it can be that. I was lost. And then, but the main thing that we were thinking at the time, without any proof, that it's probably the gallium vacancies and hydrogenated gallium vacancies, or gallium vacancies with tin complexes. Because as you consider the defect reactions like Krager-Wink reactions, it can easily show you that, okay, most probable defect we will have in the material is going to be gallium vacancy, as we add group 4 to achieve the charge balance. So, and this is my proposal at the time. So, what's happening really? So, gallium vacancies are deep level defects, and it is close. The level is close to the valence band. So, and remember that we have a very, very slow hole mobility in gallium oxide, which means as we generate electron holes, the holes are slowly moving and electrons are fast. Holes are slowly moving, which increases the possibility of holes to be trapped if there is any available trap space. And there is. Gallium vacancies are very close to the valence band. So what my proposal is at the time, okay, if we trap holes, which is most likely, then what happens is we're going to reduce the Schottky barrier a little bit because of positive charges there. And by doing that, we will also thin the barrier. So we will talk more about that. This is the peak. All things considered, with the all things that we learned, now we were like, okay, let's try now homoepitaxy. Now we can go with the expensive things. So here you see that tin gallium oxide growth on beta gallium oxide. It is 201 direction. So now we have a single crystal, tin gallium oxide. So it's 3 minutes. Okay. So now we have a single crystal, which the result is better crystal quality with tin. With tin, why I told you why we are adding tin. Tin increases the gallium vacancies, which gives us gain. So we are as we alloy tin, we achieved 35 kilo amp per watt. I got excited. So this is like for a thin film. This is not a like nanowire. This is not something that we cannot regenerate. This is a thin film, and we have 35 kilo amp per watt. This is still, I guess, the record. I'm not exactly sure. I will check. So and it is much faster because we have a single crystal now with the functional defects. So let me finalize it. We were like, okay, now we are in a good place to do a theoretical study. I'm not expert on first principles, so with our collaborators from Livermore National Lab, so they have done, we didn't give them anything. We just said, okay, do a calculation with tin addition to gallium oxide. Because, I don't want to say this, but a theoretician can calculate anything. So, so we didn't give anything. Calculate it and please give us what could be the emission spectrum. So they've done that. And they said, okay, then after the calculations, we said, okay, these are the emission spectra. They were like, okay, we have very good candidate for those. So gallium vacancies and its hydrogenated complexes and gallium vacancy and tin complexes are giving us exactly the green band and blue band. So we were like, okay, perfect. Now we can go and say that, okay, here is the experimental work, here is the theoretical work. Most likely, this is the reason why we are having extremely high gains. At the same time, faster devices. So I already told you what happened. So basically, before people were saying, so it is impact ionization, it is self-trapped holes, it is just Schottky barrier lowering. But we said no. It is most likely, I'm not like saying 100%, but most likely it is hole trapping. I'm just going to show you what happens. Let me see. Yeah, this is a good picture. So as we increase hole trapping in the space charge region, what happens is the Schottky barrier, it's called a Schottky barrier lowering effect. Schottky barrier goes a little bit down. As we put more positive charges there, the barrier goes further. That is not the only thing what happens. As it goes down, it also tends. Because remember, okay, I'll go here. The holes are moving to the contact, right? And that is the barrier, Schottky barrier. So we are moving slower. As we go along, we are getting, the population is increasing. And more holes means more trapping. So what happens is the most likely scenario is that holes are going to be trapped closer to the surface. I mean, not surface, interface between metal and semiconductor. Therefore, by doing this, we kind of have a transistor with photo-generated hole-activated transistor. So that finalizes what I would like to say. Conclusion is, I've showed you several ways to reduce the cost while having good photodetectors, and I've shown you how to tune the cutoff wavelength by alloying, at the same time reducing the cost. And also I've shown you that we have like record-breaking responsivities, but why? Why this is still most probable scenario. This is still valid. I don't know, maybe in the future, some people are going to say no and prove it. I mean, good. But yeah, next, recently, 2024, December, no, 2023, December and January, there were two papers showing that, okay, now we have an P-type material, ultra-wide bandgap material, and that is lithium gallium oxide. And so far, it seems a really good candidate, and it has a viable P-type dopability. So next, I have the plans to work with this material too. And also, rutile germanium oxide is a good candidate. And I have a collaborator in Yıldız Teknik University. We are working on it. Hopefully soon we will come with faster devices with UVC detectors. Thank you so much.
Yeah, thank you so much, Dr. Alper Ülkü. Any questions from the audience? Yeah, please.
Actually, I want to ask what is the useful range of this application?
Useful range?
Yes, you said we are catching some lights, and what is the range that we can catch?
Oh, okay, distance you mean.
Yes.
All right, so what's the range? Depends on the wavelength for sure. But if I go back to the first slide, okay. Anyway, so I don't wanna spend more time. So the range depends on the wavelength, and 280 is the highest range you will get in UVC. As you blue shift, the range is gonna reduce. So that's a very good question because that is a big limit for applications. Like if you are looking for a missile coming through, like with Mach 3, let's say. So you have a very limited time to detect it, right? That's why these detectors are usually employed in early warning systems. It's not like, okay, you detect a missile coming like 100 kilometers away. You cannot do that. But for early warning systems, especially for like helicopters and those like military applications, short distance, it's a very good warning system. Because if it warns you, there must be something. It's not noise. You know that. So that depends. The graph, the second graph, that's what I was trying to show. The second graph was for a kilometer. So the one that you've seen, the transmission, you go down to 220, you have nothing. That means like 1 kilometer is too much for 220 nanometer light, but it's not for 280.
Thank you.
Any other questions? Yes, please.
Thanks. Thank you for this great talk. I was wondering, you're adding holes, you're adding defects. Can you also structure those holes or structure those defects to increase even more the efficiency?
Probably yes, because especially if we have the defects just close to the surface, and I didn't understand what we are talking about by structuring it.
Like putting them on a, like, let's say, periodic basis, or having more like almost like a nanostructure of like defects, pattern of defects.
Probably yes. Like that way we can control them in a much better scenario. And if we can control them, definitely we can manipulate them and improve the quality for sure. That might be a good way to go with, actually. Thank you.
First, thanks for your nice talk. It was a good inspiration to what will be done with a material. You did lots of research about it. I just wonder, you said before that there's a game mechanism with hole trapping. Just wonder, this hole trapping has any downgrades? For example, it may affect lifetime, or there is any bad situation about it? I just wonder.
Yes, and that's a great question. That was maybe I showed you the last work.
Mm-hmm.
So after that, I was looking for that, and that's why it's a perfect question. So yes, we can increase the gain,
Mm-hmm.
and since it's single crystal, yes, we can have a faster device. But as we increase the gallium vacancies, what happens is we are going to have more hole trapping, detrapping. So these holes trap there, but they don't stay there. And think about this scenario. So you have photogenerated electron holes, and holes are trapped there. Yes, it reduced the barrier, exponentially increased thermionic emission, quantum field emission, and you have like you opened up the transistor, let's say. Now a lot of current is flowing, but once you turn off the light, what happens? What happens is now there is no light, there's no photogeneration. Okay, electron flow is getting slower and slower, but now you still have those trapped holes. So yes, they will detrap, but it's going to take time. So until they completely detrap, you're going to still have some signal, which is giving you as increased hold times, which degrades the performance. It limits your bandwidth for a detector.
I see. Thanks for the answer.
Any other questions? Colleagues, yeah, please.
You said it's open. You said that you covered the catching region with SN thin.
Yeah.
So this isn't cause reflectivity and loss.
Your question, if just correct me if I'm wrong. Your question is, yes, we are doing thin alloying, and no, it's not covering with tin. It is alloying gallium oxide with tin oxide to form a thin film. So yeah, the optical properties, what happens, maybe I can show you the transmission, like optical properties after the talk.
Okay, colleagues. Then I have a question. First, thank you so much for this insightful report. So it was like a detective story, actually. I like personally this kind of it's not a lecture, it's like a research intrigue, actually. Yeah, and to be continued the last slides. So that's very nice. Thank you so much. So my question is about like spectral sensitivity and prospects in it. So we started with the solar blind range, which is relatively like broad range, actually, covering like 2 orders of magnitude, I think, of wavelengths. But the detectors discussed were somewhere around 250 nanometers. What's about the shorter wave range, maybe around 100 nanometers? What are the prospects in this range?
Thank you so much. So the issue with shorter wavelengths, so I'm an engineer-minded person. So the applications are very limited for those. For instance, like now ASML is working on like, very short wavelength lithography. But for, let's say, 193 nanometer was the previous technology. So for that, we had to use nitrogen to prevent the transmission losses, absorption. So as we go higher and higher photon energies, what happens is that easily ionizes everything, meaning that the transmission is going to be very low compared to, let's say, 250 nanometer of light. So for those wavelengths, that can be used for certain functions for sure, like lithography, like other things like synthesization, especially 220, 210 is a good cleaning wavelength, so to speak, because that at 220, that doesn't harm our eye, And that also doesn't penetrate to the skin. So 210, 220, those are good for that. And for lower wavelengths, for like atmospheric applications is not possible. But for certain, again, specific applications, definitely there are. If you want to ionize things, if you want to kill a bacteria, yes, they are good for that. And it is also used in your field. I'm not so confident. RNA, DNA imaging, I think the UV range is also used in that.
Yeah, but rather 260 to 80.
Yeah. Okay. Thank you.
Thank you so much. And finally, yeah, let's appreciate our distinguished speaker. Yeah, and traditionally, so let me just share this certificate of appreciation. Yeah.
Oh.
Yeah. So I don't know how to better we can do. Yeah, and this is the certificate of it's donation. We prepared it in your name to support our students in their education and research. Thank you so much. Thank you so much for your participation. Let me just briefly introduce the next talk. Yeah, it is given by Professor Maria Krenova, representing Moscow State University, Russia. And this talk is entitled Molecular Modeling in Photophysics and Photochemistry of Biomolecules. And so, like brief introduction of the speaker. Maria Krenova graduated from the Faculty of Chemistry of Moscow State University, where she is currently a professor and the head of the Laboratory of Quantum Chemistry and Molecular Modeling. Also, she is a head of a group of molecular modeling in the Research Center Fundamentals of Biotechnology within the Russian Academy of Sciences. Her interests are focused on molecular modeling mechanisms of enzymatic reactions, as well as photochemical processes in proteins. She was awarded by a National Scholarship L'Oréal UNESCO for Women in Science, Moscow Government Award for Young Scientists, and professorship of the Russian Academy of Sciences. And also I will add to this bio some words from myself. So Maria represents a great scientific school established by Professor Alexander Nemukhin, who was a pioneer in like application of advanced computational techniques to macromolecules, to biomacromolecules, including photomolecules, and this was a great contribution. Unfortunately, he recently passed away, but his contribution to this field, to like synergy in our understanding of the photoprocesses and processes in biomacromolecules is of great relevance. So thank you so much, and I give a word to Maria, please.
Good afternoon, not good afternoon, so good morning, dear colleagues, and it's a real pleasure for me to participate in this event. And actually, I'm going to share with you some thoughts on the synergy of molecular modeling and some experimental results that complement each other. And actually, the main focus will be on different fluorescent proteins, and those are, of course, composed of proteins of different types and also different chromophores. Here, I just put 3 figures of 3 main groups of fluorescent proteins. Of course, the most known is GFP-like protein and some other members of this family that actually nowadays cover all visible part of spectrum and even near infrared. And also, fluorescent proteins that carry flavin chromophore, and also phytochromes that are not that popular, but still they have some interesting applications and their own, field of utilization. So let me first start with the methods that are utilized to compute some properties or functions of proteins. Those can be devoted basically to two classes, classical method and quantum-based method, or empirical and ab initio. It's also the same classification. And how it looks like. Here is the picture that I took from some review article, and this picture demonstrates that the model systems, I mean the protein or any biological systems like DNA or protein are of course really huge, and this peculiarity regulates the methods that can be utilized, I mean, for some description. So here on the left part of the slide, you can see the typical size of system that can be studied using quantum methods. We will talk sometime later about them, and it's usually like up to 1,000 atoms. Of course, you know that a protein or a DNA, double-strand DNA, is of course much larger, molecule. Therefore, for this purpose, usually classical methods are utilized. And what is the difference? So empirical or classical methods are based on the idea that the molecule is a set of atoms connected by covalent bonds. And also, of course, all these atoms have some partial charges, and that's all actually. So the classical force fields, I think that many of you already heard about them from some scientific papers. Actually, classical force fields are huge, databases that comprises the properties of potentials of interactions between atoms, so empirical potentials. So those are bond deformations calculated according to the harmonic potential, where the x naught is the equilibrium bond length, x is of course the current bond length, and k is the force constant. Similar formula can be utilized for angles, deformation of angles, torsion deformations, and also, of course, non-bonded particles, and also, of course, bonded particles are interacting according to the electrostatic interaction law. And also, of course, there are some van der Waals parameters that determine the size of atoms. So what are the problems of this method? Of course, these methods, classical methods, are really fast and can be utilized for really huge systems. I mean, now I think up to thousands, up to hundreds, thousands atoms can be easily calculated. But still, there are some problems, some tasks that cannot be utilized using, cannot be solved using empirical methods. So, for example, those are things related to chemical reactions. Of course, even in protein systems, many chemical reactions takes place. And if we utilize classical methods, so we determine from the very beginning, from the system setup moment, we determine which atoms are connected via covalent bonds. So, for example, if you here see the simple reaction when AB molecule interacts with C, and after that the products are BC molecule plus A. So then, from chemical viewpoint, we understand that there should be a transition state where the AB bond is already partly broken and BC bond is partly formed. Still, if we use classical force fields, we determine this AB covalent bond in the very beginning. And if we go along the reaction coordinate, that is in this case elongation of the AB bond, then we will have this monotonous curve that actually correspond to the increase of energy. So the more we extend the distance between A and B atoms, the larger is the energy. If we come from products, then of course the energy increases with the increase of the BC bond length. But the truth is somewhere in between, and we understand that in real system we should have the energy increase, then transition state corresponding to this structure with the partly formed AB and BC bonds, and then energy decrease coming to the next minimum corresponding to the products. Another limitation of empirical methods is related to the description of the excited electronic states. This is of particular interest for photochemical processes and for physical processes, and of course, some other methods should be also taken into account. So the alternative is utilization of quantum chemical description of molecular systems, and according to this model, a molecule is a set of nuclei and electrons. And actually, what is done is, so we formulate the Schrödinger equation, and then that is, and wave function. And what we do is that we find the wave function and calculate some energy properties and so on. But the problem is that quantum chemical methods are really expensive. And actually, this slide is quite old. I made it in 2009, and actually, not many things changed since that time. And still, the size of quantum system, if we perform pure quantum calculations, well, usually do not exceed several hundreds of atoms. So 1,000 atoms really already not that typical. But as we know, so we are interested in this pink region covering proteins and some other biological macromolecules, and therefore we should go from this area somewhere here. So in about 10 years ago, the Nobel Prize in Chemistry was awarded to a group of scientists who introduced combined methods of quantum and classical mechanics that combine strong points of both of these group of methods. So namely, these methods can describe formation and cleavage of covalent bond or electronic excited state due to the explicit description of the region of interest using quantum chemistry-based methods. And actually, the rest of the system is treated via classical force fields. And what is important here is that in this case, classical system contribute to the quantum system due to the partial charges, and also serve some steric restrictions to the quantum subsystem. So this allows to model biological system in a quite nice way. So this combined quantum mechanics, molecular mechanics approach is I think is one of the most utilized methods for biological systems. So it was a short introduction related to the methods, but next I'm going to show you some examples related to utilization of quantum-based methods, and also some new results, some new approaches that allow to extend understanding of the behavior of photoreceptor systems. So of course, already several tens years, theoreticians can calculate some photophysical properties of chromophores, for example, excitation energies and so on. But the problem is that, of course, there is a certain accuracy of modern methods, and therefore, if you have a set of similar systems, it is really quite difficult to differentiate them. For example, if you have a set of fluorescent proteins with similar properties, with similar absorption and emission band maximas, well, it is really difficult to calculate and to be confident of what you calculate. I mean, with respect to the, for example, position of the absorption band maximum. Therefore, the alternative approach is to quantify, to calculate some quantities that are not exactly excitation energies, but some other property of the system that can be calculated with higher accuracy and that has some physical meaning. So here is the example of the green fluorescent protein. And here on the slide, you can see the chromophore of this protein. It is a conjugated pi system composed of two rings, phenol ring and imidazolidone ring, and those are connected by bridge. It is known from the physics that the excitation energy is related to the dipole moment variation upon excitation via quadratic law in case of some media, and in a linear way if we speak about vacuum. So here is what is this DMV or dipole moment variation. Here you can see the light blue and pink areas. That is actually the electron density difference related to the excitation. So you can see that upon excitation of this anionic chromophore, the electron density is shifted from this phenolic region to this 5-membered ring. And actually these 2 points, QCT, so it is the Q is the charge, yes, CT is charge transfer, and these are body centers of negative charge transfer region and positive charge transfer region. And actually DMV is calculated as a multiplication of charge transfer, so the value of transfer charge and the distance between these two buried centers. So, and it was found that indeed from calculation you can get the interrelation between the excitation energy in protein and this calculated DMV value. So here are 2 examples, and the left one is related to some model systems of these GFP-like chromophore with indifferent surrounding in like gas phase, and here you can see the linear relation. So this is a linear Stark effect, and the right figure is related to the GFP-like proteins in solution. I'm sorry, chromophore buried in protein and in solution. And here you can see the quadratic dependence. So therefore, the message here is that modern methods are sometimes not accurate enough to directly calculate the quantity of interest. In this particular case, it's the excitation energy. Still, some other quantities can be found, and these quantities can be calculated with higher accuracy and can be utilized as descriptors of a set of similar systems. So another important example of the utilization of quantum chemistry-based methods is the estimation of the efficiency of first resonance energy transfer pairs. I think many of you know that so a powerful tool to evaluate, for example, some events, like for example enzymatic activity or maybe some others, is utilization of thread pairs that have different photophysical properties depending on the distance between the donor and acceptor. For example, if you have a donor and acceptor molecule and those are located close to each other, then excitation of donor results in the non-radiation radiationless energy transfer to the acceptor and emission of acceptor. So you can observe absorption of donor and emission of acceptor. But for example, if these two proteins are connected by a linker that carries, for example, some oligopeptide fragment that is that can be cleaved by some protease, you can measure its catalytic activity. So the protease comes to this linker, cleaves it, and then donor and acceptor comes from each other. I mean, apart from each other. Then the thread efficiency, of course, reduces, and what you see then that if you excite a donor molecule, then the fluorescence also comes from the donor molecule. So, but important point is that not only the distance between donor and acceptor chromophore are important for the thread efficiency, but also another important thing is the orientation factor that is calculated from the transition dipole moment of donor and of acceptor chromophores. And these quantities can be actually evaluated mainly only from the quantum chemical based calculations. And what is important here, that this orientation factor that directly comes to this first radius is the value that is changing from 0 to 4. So this means that you can have a nice thread pair that is, nicely suits from the point of view of photophysical properties. I mean that they have, for example, huge overlap between the fluorescence of donor and excitation of acceptor, but in case the orientation factor is low, so in case these two proteins are oriented in the wrong way relative to each other, then the thread efficiency anyway will be low. Therefore, so this is another example where utilization of quantum chemistry-based method can really deepen the understanding and can assist in obtaining an efficient thread pairs. So we all understand that biological processes occur in solvent and at some temperatures like room temperature. Therefore, it is really important to understand not only the static picture but also the dynamic behavior of the biomacromolecules. Therefore, the next part of my talk will be devoted to the molecular dynamics simulation and to the system evolution to the system evolution. So here is the figure that represents the typical time scale of different processes like bond vibrations, rotation of some side chains, and also protein folding, and so on. So nowadays, the molecular dynamics simulation with classical potentials that we already discussed in the very beginning of the talk usually covers the time scale between nanoseconds and microseconds. So the typical trajectories that can be obtained now on GPUs are of so several microseconds. So what is molecular dynamics? Actually, it's the way. So it's the method that solves Newton's equations of and obtain trajectories. So in the very beginning of the simulation, you should choose the initial geometry configuration, so initial set of coordinates of all atoms, and also you should assign velocities of each atom according to the temperature of the entire system. Then you calculate in some way the forces that are the resulting forces that act on each atom, and then you obtain the acceleration, and then you can integrate these equations and obtain a set of coordinates and velocities at the next moment of time. So these simulations broaden the understanding of the biological system behavior, and actually here is some data that demonstrate the following thing. Actually, it's not only about the computations, but also about any experimental field, that some really new, revolutionary new things occur when you have then you get to the next step of the development of some technique. Here I mean the following, that several years ago, the powerful GPUs were introduced, and since that, the revolution in molecular dynamics simulations happened. So it means that previously it was necessary to utilize some supercomputers, and also even in that case the simulation time was really quite small and not enough to obtain some conclusive results. But nowadays GPUs are really cheap, and they can be put into not only into the supercomputer but also to the particular desktop, and fast rapid simulations can be obtained. Of course, it is also important that software is also already optimized for these GPUs. So next I will show you some data related to the analysis of these trajectories. I mean that proteins are complex systems, and of course just visual inspection of the molecular dynamics trajectory, I mean analysis of the set of frames of this trajectory, is usually not enough and not deep enough to understand what is going on. Moreover, big data analysis can indeed add some new understanding. So here is the short introduction to the dynamic network analysis that allows to calculate correlation of movements of some groups of atoms in the entire system. So I'm not going to talk much about the details of this method, but what is important here, that this method allows to understand which groups of atoms are moving so-called together or correlated, and which are not dependent on each other. So here is the cross-correlation map, and you can see the darker regions, dark red or dark blue, are related to the regions that with correlated motions. So these are, of course, regions where, these are, of course, neighboring residues, and also some structural elements that are properly located in the space. So here is the some protein molecule, and this edges, these blue edges represents the interacting nodes. So the nodes that are moving that are characterized by correlated movements. And on the right slide, on the right part of the slide, you can see the same picture, but with the weights added to the representation. So it means that if you have this large weight, and so the movement is more correlated, and you have these thin edges, then the movements are less correlated. What is more important here is that not only correlation of movements can be obtained, but also a huge protein can be divided into communities. So this means that the protein is divided to some parts, and these parts are characterized by stronger connections, stronger correlations of movements inside of this community compared to the neighboring parts. So this this method well, initially it was mainly proposed for understanding the influence of allosteric interactions in enzymes, but then it was really successfully utilized to many other tasks. So this is the picture that demonstrates the initial purpose of this community analysis and transmission, signal transmission path calculation. So this means that you can suggest the initial point and the final point you're interested in. For example, here the initial point can be the potential binding site, and here another point is, for example, a part of the active center. So, and then you can see how this signal from this part goes to the final point, destination point. And actually, this is of course mainly interesting for the enzymes, but I will show you some results related to the dynamic network analysis of photoactive proteins. So the first one will be devoted to the photophysical properties of GFP, and also I will show you how the signal transduction from the photoreceptor to the catalytic domain can influence the catalytic activity of the latter one. So let me first show you the fluorescent proteins with beta barrel structure. So those are GFP-like proteins. And here is the figure that represents the fluorescent protein SARS-40 that was found in that is interesting and quite well. It's not typical due to its really due to its photophysical and photochemical processes. First of all, it can be initially it carries green chromophore, but it can be irreversibly oxidized to the red form. So actually, from the chemical viewpoint, it means that this CN bond is cleaved, and this single bond, this CN single bond, is transformed to a double bond. So like here. And then, of course, the conjugated pi system is elongated, and in the red form, it already comprises the side chain of the histidine residue. And of course, this extended pi system is characterized by the red-shifted absorption and emission. So in green form, the protein is characterized by 510 nanometer excitation and 520 nanometer emission, and for red form, both of these values are about 60 nanometers shifted to the red part of spectrum. Also, these proteins are characterized by reversible photoisomerization of both red and green forms. So this means that the ground or the most stable state of these proteins, of these chromophores, are characterized by cis form, like here with the green chromophore, but it can be photo switched upon irradiation to the trans form. In trans form, this chromophore is already in the neutral state, in the neutral form. Here it was in the anionic state, and of course this form is a so-called dark state or non-fluorescent form. And of course, after some time, it can convert back to the on or cis state. So, of course, it's interesting to understand what is the structural or dynamic background of different properties, why some chromophores can isomerize and some others cannot. And from the experiment, it is known that the red form of the chromophore can isomerize only if either of these residues, either phenylalanine or methionine, are replaced by some other smaller residues. But what is interesting here that these residues do not prevent the chromophore from isomerizing in the green form. That is really strange, because the isomerization takes place here, and the green and red forms differ in this region. So therefore, of course, it was quite difficult to obtain some solid theoretical background on this observation, and static picture did not clarify anything. And therefore, we decided to perform this dynamic network analysis. So it means that we performed large molecular dynamics trajectories and analyzed these regions of correlated motions. So we found quite an interesting thing, that the isomerization occurs in case of species with the phenolic part of the chromophore and this former side chain of histidine residue belonging to this same community. So in this case, the isomerization occurs. If the phenolic part of the chromophore and the 5-membered ring of the former histidine belongs to different communities, then this systems do not isomerize. So here are some other examples of the system without isomerization of the red form of the chromophore. So those are M-SARS-40, is a monomeric variant of the SARS-40 protein, and also M-SARS-40 with a distant mutation of cysteine residue to the asparagine. And in both cases, we can see that the community that comprises the phenolic part does not comprise this 5-membered ring. Contrary, for the system with isomerization in the red form, we can see that this phenolic part and 5-membered ring belong to the same community here and in the middle picture and on the right part of the slide, so in all considered systems. So we were really wondering whether this is valid, this can be utilized for the green form, and it was found that for all proteins, of the SARS-40 family, the phenyl fragment of the chromophore is in the same community with the side chain of the histidine residue, and it is really quite unexpected result, because these fragments are connected by flexible aliphatic linker, this region, and so still those are belonging to the same community. Another example that I'm going to show you is the optogenetic system with the flavin-containing photoreceptor domain. And actually, I think many of you know that optogenetic systems are really very different and are developing to control the cellular processes. And what I'm going to show you is the soluble cyclases. So those are proteins that convert ATP to the cyclic AMP and pyrophosphate. And actually, it is known that for some bacterial systems, the photoreceptor domain can influence in the catalytic activity of the cyclase domain. So here is the bacterial photoactivated adenylyl cyclase, BPAC. And this is a protein that comprises the BLAF photoreceptor domain. So this domain is comprises the flavin chromophore. And here is the catalytic domain, adenylyl cyclase. And the entire system exists in the dimeric form. So this BPAC is a dimer and is composed of 2 photoreceptor domains and 2 catalytic domains. It is known that for this particular optogenetic construct, the irradiation of BLAF domain increases catalytic activity of the adenylate cyclase domain for about 300 times. Actually, it's really quite a huge value. So what is going on upon excitation? Indeed, many research, a lot of research was done to understand what is happening upon the excitation, and now the hypothesis is more or less sort of approved by computational and experimental results. And what is going is the following. So this is the flavin chromophore, and this is a glutamine residue that interacts with the chromophore and with a tyrosine residue. So actually, upon excitation, a set of events occurs, and then the tautomeric form of glutamine is obtained, and it is rotated along this CC bond, single bond. So then this means that the main difference between the dark state and light state after the photo process is the conformation of the side chain of glutamine, whereas the chromophore itself is not changed. So the question is how this signal from this domain, these local changes, affect the rate constant in this domain. So let us first consider this catalytic domain. So actually the chemical reaction is quite simple. It is the conversion of ATP to CAMP and pyrophosphate. So this OH group attacks phosphorus atom that leads to its cyclization, and so the PPI is released. So static picture of this complex did not clarify the mechanism of the single transduction from here to this catalytic region. Therefore, molecular dynamic simulation of the entire complex were performed to find some maybe possible pathways or some other stuff, and so what was done is the following. So 3 model systems were constructed. So those are wild type system in the dark and light state that carries catalytic domain with different activity, and also this mutant form with the substitution of tyrosine residue to the phenylalanine. We can see here, so this mutant variant does not have this OH fragment, and this of course affects the photochemical reaction pathway, and no changes likely happen in this region in the Y7F variant. So according to experimental data, this variant is independent on light radiation. So here are three systems that we considered. So those are dark and light state of the wild type protein, and also this variant that is not sensitive to radiation. So here is what I told you about the modern opportunities. Related to the GPU utilization. So the typical trajectory length was 1 microsecond. It's really quite long and quite enough to demonstrate some molecular events. And the system is really quite huge. It's 100,000 atoms. And this is a pure classical calculation with utilization of classical force fields. Charm force fields is one of the most sort of popular and widely used force field for the protein, and its extension to the organic molecules, charm general force field, that is utilized for the chromophore, for the Flavin chromophore. So what we got? The important point is that we tried to find some pathways similar to the allosteric regulation from the photoreceptor domain in the top to the catalytic domain in the bottom of the slide. So what we found is that there are some pathways from the glutamine residue to the tyrosine and so on, and come into some different residues in the active site. And what is important here that so these pathways comes to the arginine residue, and we will focus on it on the later slides. And importantly, according to the experimental data, it is known that residues lysine 75 and histidine 266 are important for this pathway, and we also observe these residues in our simulations. So what we can find and how we can characterize the arginine residue of the catalytic domain. Actually, it was found that it carries different conformations in dark and light state, mainly due to the differences of conformation of this asparagine residue. So here are distributions of dihedrals of this arginine residue, and we can see that this so the blue one is the dark state and the red one is the light state, and these populations are really located in different parts of the graph. And what is interesting here is that this magenta curve that is related to the mutant variant demonstrate two different populations with comparable weights, so that both dark and light state populations are presented. So from let us see at the active site of the protein and actually how the conformation of the arginine residue affect the enzyme substrate complex. So in the dark state, the arginine residues is oriented to the beta phosphate group of the substrate of the ATP, and in the light state it is located closer to the alpha phosphate group. It is important because the chemical reaction is initiated by the nucleophilic attack on phosphorus atom and cleavage of the PO bond. And of course, location of the arginine residue here stabilizes the alpha phosphate. So that should decrease the energy barrier and also stabilize the reaction products. So development of computational tools and so hardware allow us to perform not only static quantum mechanics, molecular mechanics simulations, but also to calculate trajectories with QMMM potentials. Therefore, we perform the careful analysis of enzyme substrate complexes, and it is important because we can obtain not only a certain structure but also distributions. That is really sometimes very important. For example, here on the lower panel, you can see two distributions, green one and blue one, and green distributions is much more narrow. And so I mean that if you get only one structure, it will be somewhere here, and it is really rather representative for the entire distribution. Still, if we consider this blue one, this distribution is really wide. And for example, if you have only one structure, it can be in this region, and you have no information about the rest of the parts and so on. Therefore, now we are trying to switch, and we are switching to QMMM simulations with, I mean, in dynamic variant, but not in a static one. So this can be done on common computers with GPUs, with gaming GPUs, and we utilized TerraChem software package that is optimized for GPUs. So let me show what can be done here. And here is the distribution of the nucleophilic attack distance for the so in dark and light states, so distance between this oxygen and phosphorus atom. So even analyzing only enzyme substrate complex, we can see that the complex itself is really different. It is tighter and more rigid for light state, that is red curve, and more loose and flexible in the dark state, it is a blue curve. Similarly, the distribution of hydrogen bond lengths is also different. So the hydrogen bond in dark state is formed between the proton of the OH group of the nucleophile and an oxygen atom of the phosphate group, and actually it means that in this configuration, of course, the nucleophilic attack of the oxygen atom on the phosphorus is quite difficult. Still, in light state, this proton from the nucleophile is oriented to the water molecule. That is a good candidate for as a proton acceptor. So similarly, in light state, this proton wire is more pronounced, and the proton that is moved from the nucleophile can then can facilitate the proton movement from the water molecule to either of these proton acceptors, either of these aspartic acids. So we of course, we performed explicit calculations of energy profile, and what we see here is indeed that in light state, the process happens with much lower energy barrier. I'm sorry here for Russian notation, but anyway, it's about 9 kcal per mole, and here the energy barrier is about 15 kcal per mole, and actually these energy profiles demonstrate that the understanding that we got from the enzyme substrate complex dynamics can be is valuable for further understanding. So the last short example of the utilization of the dynamic simulation with QMMM potential is related to the long stalk shift fluorescent protein, LSSM scarlet 2. So it's a protein that exists, that chromophore exists in the neutral state. So it is characterized by, it's a misprint. Of course, related to this emission. Emission is, of course, in some other region. So the excitation occur in the neutral form. Therefore, it's quite considerably shifted to the blue part of spectrum. And actually, upon excitation, it is likely that the proton is transferred from the chromophore to the aspartic acid of the protein, and the emission already occurs in the anionic form. So this is, of course, the hypothesis that can be just obtained from the spectral features. But the direct demonstration of this mechanism can be done only using molecular modeling tools. So here is the graph representing the results of molecular dynamic simulation with QMMM potential in the excited state. So upon vertical excitation, so here is the blue circles are S0 state in neutral form, and upon excitation the geometry configurations are quite similar, but so still in the neutral form. But upon evolution in the excited state, the proton from the chromophore is transferred to the aspartic acid, and then we can see this red fluorescent state with the proton being already on the aspartate, and with the much lower energy gap between the ground and excited electronic states. So with this, I'm going to end my presentation. And as for the conclusion or take-home messages, I want to tell you that modern molecular modeling tools are really quite powerful and can add some insights or some additional understanding on what is observed in the experiment. And of course, modern science is very interdisciplinary, and so combination of these methods together really can deepen their understanding. So thank you very much for your attention. I'm happy to answer the questions.
Any questions, colleagues? Yeah. Okay.
Thank you very much, Maria, for that very rich talk. I have several questions, but I'll limit myself to the first one that appeared, and that was in connection with the dipole moment variations.
Mm-hmm.
You said you can calculate them much more precisely than the excitation conditions. Why is that? What is the ingredient that you need for the excitation condition for the dipole variations?
I'm sorry, I cannot hear the end of the question. So I got that it's about dipole moment variation upon excitation, and you are asking about the reason of different accuracy of estimation of energy and this value. Would you kindly repeat the question? I'm sorry, but I really don't hear you. I see that you're asking, I mean, from the video, but I can.
Maybe I can help. So the question was, why it is easier to accurately estimate dipole moment transitions than the excitation energy gaps?
Yeah, okay. So the wave function itself and corresponding electron density is generally better better estimated. Well, just a moment. Okay, it's not that thing. The energy, the determination of energy is the limitation of energy accuracy of, I mean, as not as one gap is like 0.1 electron volt, and this corresponds to about 20 or even 30 nanometers, depending on the, I mean, on the part of the visible spectrum, and the dipole moment variation upon excitation is a more, how to say, it is well, I think that the wave function actually can be determined more precisely than the corresponding energy. So it means that when you obtain a wave function, then you should calculate the energy of the corresponding state using some approximations. So the wave function is already obtained, and the corresponding electron density is calculated as a square of the wave function, and then the energy is estimated. So it's like a more complex procedure. Therefore, the errors in the wave functions are somehow multiplied and accumulated more when moving to the estimation of the precise energy values. And also it is important that when you calculate the energy of several electronic states, the approximations are usually better for particular state, but not for all states. And then, for example, you can precisely determine the energy of the ground state, but within the same model, the excited state will be, the excited state energy will be determined with larger error. So this is the answer, I think.
How do we choose them? Is it like a manual choice, or we base our choice on some preliminary, maybe lower resolution molecular dynamics? How do we choose these communities, intraprotein communities? Yeah.
Okay. This is actually the quite automated procedure. So it means that first of all, you calculate correlation between every pairs of nodes. So I mean every atoms that you included in your model, and then the calculations. So then the algorithm choose the groups that are characterized by larger correlation within the group compared with the neighboring parts.
Mm. Thank you so much. Yeah, the question. Yeah, we have the question. Mikhail?
Sorry, I actually had a follow-up question. Well, it wasn't a follow-up question initially, but now it is. So about this community, so you find groups which are not correlated. Do you also have some kind of frequencies which they interact with each other, or can you find anything like how different communities interact with each other?
Could you repeat the end of the question? I'm sorry, but it's really not some.
Maybe this microphone is more useful. I think there is an issue with the microphone.
Yeah, this microphone is really much better. Yeah.
Okay.
So I had a follow-up question on these communities. Is there any? Could you find any interaction or frequencies in which the communities interact with each other to get more information of like the total system, let's say?
So you mean some particular interactions, yeah?
Yes.
Actually, it's really quite a tricky thing because, of course, this dynamic network analysis was not, in my case, limited only to this particular tasks that I told you. And actually, what I observed myself is that, for example, you have a huge protein and a distant amino acid substitution that, in my opinion, should not anyhow, affect the property. Still, it somehow, influence and, varies this community, separation to the community. So I cannot say that some specific interaction can be obtained because even from the pure dynamics, even if you look at some contacts of neighboring residues, you cannot see with your eyes any pronounced differences. So this is mainly about the big data analysis. So it's not that easily visible or easily understandable. Unfortunately, it's really this popular nowadays thing that when you have big data and you just put it all together and get some not evident relations within this data, and this is unfortunately partly this moment. So not always, for example, for this BPAC system, we found indeed these different conformations of arginine, but for fluorescent proteins we did not quite get what was really different between these proteins that are able and are not able to isomerize.
Okay, any other questions, folks? That's it, I think. Let's appreciate our speaker.
Thank you very much. It was a real pleasure to participate, and I wish you all the best for today. You have some more lectures today.
Thank you so much, Maria. So to express our appreciation, we would like to share a certificate of our appreciation to you. And also there is, so let me show one moment. There is a donation certificate we prepared in your name to support our students who are starting their careers in photonics. Thank you so much again.
Thank you very much. Thank you.
Welcome again. I'm the chair of this session. My name is Metin Tan. I'm a research assistant in Photonics department. And our next speaker is Talha Kuru. Let me introduce him to you. He got a biotechnology BSc and MSc from Selçuk University in 2020 and 2023. Talha Kuru works as an R&D specialist at YEO, and he is also a PhD student in the biotechnology department at Selçuk University. He worked on R&D projects for green hydrogen production, biogas production, and power-to-gas systems. He conducts the design and synthesis of inorganic semiconductor catalysts for photocatalytic, electrocatalytic, and piezocatalytic hydrogen evolution systems. Moreover, using advanced structural, morphological, and electrochemical characterization techniques, he enlightens production mechanisms for hydrogen production systems by the synthesized catalysts. By developing national and international projects, he designs processes to bring different hydrogen production systems to an industrial scale. So let's have you here, Talha Kuru, please. Okay. The stage is yours. Thank you.
İsmim doktora öğrencisiyim. Aynı zamanda YEO teknoloji firmasında Ar-Ge uzmanıyım. Bugün size kısa bir firma sunumu yapacağım ve fotonik bilimiyle alakalı bizim de yapmış olduğumuz çalışmalar var. Fotokatalitik hidrojen üretimi üzerine ve onun endüstriyel ölçeklendirilmesi üzerine bir sunum gerçekleştireceğim. Firmamız aslında ilk slayta gelecek olursam 400'den fazla proje tamamladı şu ana kadar. 1 milyar doların üzerinde bir hacmi var ve İstanbul borsasında işlem görmekte. 30'dan fazla ülkede projeler gerçekleştirdi ve 3 kıtada iş yapmakta. Ülkelere bakacak olursak Avrupa ve Orta Doğu özelinde aslında bir dağılım görmekteyiz. Aynı şekilde Afrika'da ve Amerika Birleşik Devletleri'nde de iştiraklerimiz bulunmakta. Çalışma alanımız aslında yenilenebilir enerji üzerine ve elektrifikasyon ve otomasyon üzerine gerçekleştiriyoruz projelerimizi. Farklı alanlarda çalışmaktayız. Enerji depolama sistemleri, RIP Battery aslında bizim bir alt kuruluşumuz. Ben de o firmada çalışıyorum. Özellikle yeni batarya teknolojilerini geliştirmek üzerine bir stratejimiz var. İYTE'de de Niket, Teknokent'te Niket firmasına aynı şekilde ortaklığımız bulunmakta. Güneş enerjisi, rüzgar enerjisi ve diğer farklı yenilenebilir enerji alanlarında elektrifikasyon ve otomasyon işleri yürütmekteyiz. Aynı şekilde anahtar teslim çeşitli santraller tasarlayıp üretim aşamasına getirdiğimiz zaman RIP Battery'den farklı olarak az önce bahsetmiş olduğum Niket firması yapay zeka kullanarak farklı katot malzemeleri tasarımını gerçekleştiriyor. Onun haricinde elektrolizörler için membran üreten iyon membran gibi bir firmamız daha bulunmakta ve aslında hidrojen enerjisi ile birlikte bütün yenilenebilir enerji alanlarında çalışmaktayız. Sistem entegrasyonu üzerinde Türkiye, Özbekistan, Hollanda gibi ve diğer farklı Avrupa ülkelerinde çeşitli operasyonlar gerçekleştirmekteyiz. Baktığımız zaman Türkiye'de ve diğer ülkelerde aynı şekilde hem batarya üzerine hem de yenilenebilir enerji üzerine farklı çalışmalar gerçekleştirerek ülkemizin yenilenebilir enerji konumunu güçlendirmeye çalışmaktayız. Şu ana kadar 1.2 gigawatt ölçeğe sahip güneş enerjisi projeleri geliştirdik. Son 5 yılda 588 megawatt pik ölçeğinde aynı şekilde yenilenebilir enerji üzerine solar panel sistemleri tasarladık. Baktığımız zaman şu ana kadar 25 tane projenin tasarımını gerçekleştirip tamamladığımızı söyleyebilirim. Başta Türkiye, sonrasında sıralama şu şekilde Bulgaristan, Romanya ve Amerika olmak üzere devam eden bir kurulu gücümüz var. Özellikle solar paneller özelinde. Doğrudan müşterilerin çözümlerine yönelik operasyonlar gerçekleştirmekteyiz. Anahtar teslim projeler gerçekleştirmekteyiz enerji santralleri kurulumu konusunda. Aynı şekilde elektrifikasyon ve otomasyon konusunda da mühendislik hizmetleri vermekteyiz. Burada gerçekleştirdiğimiz otomasyon, elektrifikasyon, dijitalizasyon gibi farklı konularda gerçekleştirmiş olduğumuz yine aynı şekilde elektrik dağıtımı üzerine çalışmalar bulunmakta. 1500 megawattın üzerinde proje geliştirdik şu ana kadar. Aynı şekilde 500 megawattın üzerinde de rüzgar enerjisi üzerine farklı ülkelerde ve şehirlerde çeşitli rüzgar tribünleri tasarımını gerçekleştirdik ve anahtar teslim olarak aynı şekilde tamamladık projeleri. Baktığımız zaman sadece rüzgar ve güneş panelleri özelinde değil, aynı şekilde jeotermal ve biyokütle, biyogaz gibi farklı konularda da çalışmalar gerçekleştirmekteyiz. Burada farklı ülkelerdeki gerçekleştirmiş olduğumuz ve ülkemizdeki çalışmaları görmekteyiz. Aynı şekilde atık su tesisleri de yapmaktayız. İstanbul Büyükşehir Belediyesi ileri biyolojik atık su merkezinde aynı şekilde projelendirmekteyiz. Çimento ve madencilik konusunda da aynı şekilde eti madenle çalışmaktayız. Onun haricinde farklı projeler gerçekleştirmekteyiz. Bugünkü asıl konu başlığım, ben Ar-Ge bölümünde çalışıyorum demiş olduğum gibi. Ar-Ge projelerinden bahsetmek istersem fotokatalitik ve fotoelektrokimyasal hidrojen üretimi üzerine çalışıyorum. Bunların haricinde elektrokatalitik ve elektrokatalitik hidrojen ve amonyak üretimi üzerinde de farklı projeler geliştirmekteyiz. Genelde baktığımız zaman firmamızın genel prensibi karbon ayak izini azaltmak üzerine olduğu için biz de yeni ve geliştirilmesi gereken farklı aslında akademik düzeyde olan şu anda çalışmaları projelendirip bunların Ar-Ge'sini yapmaktayız. Fotokatalitik hidrojen üretimi de bunlardan bir tanesi. Hidrojen enerjisine bakacak olursak şu anda %96'sı çeşitli fosil yakıtlardan elde edilmekte ve sadece %4'ü elektroliz yoluyla elde edilmekte. Bu da aslında oldukça düşük bir oran ve hidrojen enerjisine bakıldığı zaman temiz olması ve herhangi bir karbon ayak izi olmaması bizi bu alanda daha fazla çalışmalar yapmaya yönlendirmekte. Hidrojenin elde ediliş yöntemlerine baktığımız zaman gri, mavi, turkuaz ve yeşil olarak görebilmekteyiz. Bunlar aslında renk şeyleri, isimlendirmeleri. Bu neye göre belirleniyor? Elde ediliş yöntemleri ne kadar karbon ayak izi bıraktığına göre belirleniyor. Baktığımız zaman green hidrojen doğrudan elektrolizi içine alan ve yenilenebilir elektrikle üretilen hidrojeni isimlendirmek için kullanıyoruz. Gri hidrojen ise fosil yakıtların reformasyonu yoluyla aslında elde edildiğini söyleyebiliriz. Fotokatalitik hidrojen üretimi yarı iletkenlerin ışık altında ışık absorpsiyonu gerçekleştirerek foto uyarılmış yükler üretmesi yoluyla water splitting, su ayrıştırma reaksiyonunu katalizlemesiyle gerçekleşiyor temele baktığımız zaman. Bunun için uygun bant aralığı ve uygun bant pozisyonları gerekli. Fotokatalitik hidrojen üretiminin şöyle bir avantajı var. Doğrudan güneş enerjisini, solar enerjiyi kimyasal bağlarda depolayabilmemiz olanak sağlamış oluyor. Aynı zamanda yüksek saflıkta bir hidrojen üretimi de gerçekleştirmiş oluyoruz. Bu da ayrı bir problem çünkü farklı proseslerden çıkan hidrojen üretim sonucunda bunun saflaştırma membranlarıyla saflaştırılması gerekiyor ama fotokatalitik hidrojen üretiminde elde ettiğimiz hidrojen yüksek saflıkta olduğu için herhangi bir saflaştırmaya maruz bırakmadan doğrudan kullanılabilir. Lab ölçeğine baktığımız zaman, laboratuvarda gerçekleştirdiğimiz zaman bir solar simülatör kullanıyoruz. Solar simülatörler güneş ışığını simüle ediyor ve belli bir bölgeye sadece güneş ışığını göndermiş oluyor. Buradan da biz aslında laboratuvar ölçeğinde solar hidrojen verimini hesaplayabiliyoruz. Tabii bu ölçeklendirilmemiş hali. Biz burada sadece aslında katalizörlerin katalitik aktivitesine ve farklı elektron vericiler ortamlarında nasıl davrandığını eğer kullanıyorsak boya maddelerinin aynı şekilde katalitik aktivitesini ve ışık absorpsiyon aktivitelerini inceliyoruz. Mekanizmaya bakacak olursak yarı iletkenler ışığı absorpladıktan sonra elektron ve hol çiftlerini ayırarak elektronların foto uyarımına sebep oluyor ve iletkenlik bandına transfer oluyor. Burada değerlik bandında suyun oksidasyonu sonucunda moleküler oksijen üretiliyor. Aynı şekilde buradan oluşan protonlar da iletkenlik bandında elektronlar tarafından hidrojene indirgeniyor. Burada genel mekanizmayı görmekteyiz baktığımız zaman. Sistemi etkileyen parametrelere bakacak olursak optik ve elektrokimyasal özellikleri katalizörlerin. Bunlar neler? Bant aralığı çok önemli yarı iletkenler için fotokatalitik hidrojen üretiminde. Suyun ayrışma reaksiyonun için elektrokimyasal gereksinimlerine bakacak olursak redoks potansiyelleri. 1.23 ve 0 elektron volt oldukça önemli. Yani bant aralığının 1.23'ten daha dar olmasını bekleyemeyiz. Aynı şekilde güneş ışığını absorbedebilmesi için de 2.8 elektron volttan daha dar olmasını bekliyoruz. Yani daha geniş olduğu zaman yüksek rekombinasyon oranı sebebiyle gerekli foto uyarımı gerçekleştiremediği için foto uyarılmış yüklerin üretimi söz konusu olmuyor. Ortamın pH'i da şu açıdan önemli. Elektrokimyasal gereksinimleri bu şekilde değiştirebiliyoruz ama buna ilave olarak asıl sebep kararlılık. Kararlılığa baktığımız zaman yüksek alkali ve yüksek asidik ortamlarda düştüğünü görebiliyoruz. Bu da korozyona bağlanabilir. Zayıf alkali ve nötrale yakın pH'lar tercih ediliyor genellikle baktığımız zaman. Kararlılık ve tekrar kullanılabilirlik. Biz laboratuvarda gerçekleştirmiş olduğumuz çalışmaları ölçeklendirmeye kattığımız zaman kararlılık ve tekrar kullanılabilirlik bizim için oldukça önemli. Eğer bir katalizör çok yüksek katalitik aktivite gösteriyor dahi olsa, kısa sürelerde bozuluyorsa ve tekrar kullanılamıyorsa biz bunu endüstriyel ölçeğe taşıyamıyoruz. Elektron donör seçimi, asıl hedefimiz doğrudan suyun ayrıştırılması ama katalitik aktivite bazen buna müsaade etmiyor. Çünkü doğrudan suyu kullandığımız zaman hidrojen üretim verimi oldukça düşük kalıyor. O yüzden biz de farklı elektron vericiler kullanıyoruz. Bunlar neler? Zayıf organik asitler, askorbik asit, laktik asit gibi ve bunlara ilave olarak kısa zincirli alkoller, metanol, etanol gibi. Bunların haricinde triazonamin kullanıyoruz baktığımız zaman ve etta gibi farklı kimyasallar da kullanılıyor. Burada sayamadığım daha birçok elektron verici kullanılıyor. Bunlar neye göre belirleniyor? Katalizörlerin aslında elektrokimyasal yapısına ve bu elektron vericilerin oksidasyonu sonucunda valans bandı elektronlar ile destekleyebiliyor olmasına göre karar veriyoruz. O da aslında valans bandla ilişkili bir durum. Işık kaynağı, biz laboratuvarda tabii çoğunlukla solar spektrometre kullanıyoruz ama bakıldığı zaman UV ışık da kullanıldığını görebiliyoruz. Biz doğrudan bu sistemi eğer endüstriyel bir ölçekle ilişkilendireceksek güneş ışığını kullanmamız önemli. Fotoelektrokimyasal hücre aslında hem endüstriyel açıdan hem de laboratuvar ölçeği açısından baktığımız zaman yüksek ışık geçirgenliğine sahip bir malzeme tercih edilmesi gerekiyor. Bu da çoğunlukla kuvars hücreler kullanılıyor. Atmosfer şöyle, eğer oksijen zengin bir ortamda gerçekleştiriyorsak reaksiyon gerçekleşmiyor. Oksijen indirgenmesi gerçekleşiyor baktığımız zaman. Burada esas olarak oksijenin uzaklaştırılıp genellikle inert gaz ortamı yaratmamız gerekiyor. Protonların hidrojene indirgenebilmesi için. Akışın tipi ve hızı, bu da aslında kütlenin azaltımı konusunda önemli. Türbülent bir akış bekliyoruz. Çünkü eğer reaksiyon ortamında katalizör partikülleri homojen bir şekilde dağılıyorsa reaksiyonun katalitik aktivitesi yüksek olarak elde ediyoruz. Ama ancak eğer laminer bir akış söz konusuysa hücrenin içerisinde farklı yerlerde çökmeler meydana geldiği için ışık absorpsiyon aktivitesi düştüğünden dolayı burada katalitik aktivite de aynı şekilde düşüyor. Yüksek akış hızlarında da katalizörün kararlılığını koruyamadığını görüyoruz. Farklı stratejiler var fotokatalitik hidrojen üretimini geliştirmek için. İlki boya ile hassaslaştırma. Bant aralığının belli bir seviyede olması gerektiğini söylemiştim. Çünkü görünür ışık, yani güneş ışığıyla ışık absorpsiyonu yapabilmesi için ve foto uyarılmış yükleri üretebilmesi için eğer bir katalizör bant aralığı buna müsaade etmiyorsa titanyum dioksit gibi örneğin biz burada farklı boyalar kullanıyoruz. Işığa hassaslaştırıcı. Boyar madde foto uyarılmış yükleri üreterek onun iletkenlik bandına aktarıyor. Burada kullanmış olduğumuz boyalara baktığımız zaman ksenten temelli boyalar kullanılmakta. Bunlar eosin, eritrosin, rodamin gibi farklı boya türevleri. Bunlar tabii reaksiyon ortamına çözeltisine ekleniyor. Farklı boya türevleri doğrudan katalizöre bağlanarak da çalışılabiliyor. Örneğin fitolesyenler gibi, perilenler gibi farklı boya maddeler doğrudan katalizöre bağlanarak da çalışmalar gerçekleştirilebilir. Bu da aslında doğrudan ışık absorpsiyonu gerçekleştirebilen bir sistem yaratmamıza olanak sağlıyor. Buradaki problem de şu aslında: organik boyalar ışık altında belli bir süre sonra bozulduğu için yine sisteme bir kararsızlık unsuru olarak ekleniyor. Bir diğer yöntem kokatalizör mühendisliği ile katalitik aktivitenin iyileştirilmesi. Burada reduction kokataliz ve oxidation kokataliz kullanarak aslında katalizörlerin katalitik aktivitesini arttırmak mümkün. Bunlardan kasıt ne? Molibden sülfür gibi, platin gibi farklı protonların absorpsiyonuna müsaade edecek indirgenme katalizörlerinin kullanımı söz konusu. Aynı şekilde oxidation kokatalizör olarak da kobalt oksit ve benzeri yarı iletkenler belli bir oranda katalizörün yüzeyine katkılanarak çoğunlukla depozisyon yöntemini tercih ediyoruz. Özellikle reaksiyon ortamında depozisyonundan bahsedebiliriz. Fotodepozisyon gerçekleştiriyoruz. Bu şekilde katalizörün katalitik aktivitesini arttırmak mümkün. Bir diğer yöntem, şimdi belli bir redox aralığı vardı. 0 ve 1,23 olmak üzere iki basamaklı bir reaksiyon olduğundan dolayı. Bu katalizörler aslında baktığımız zaman şimdi hem görünür ışığı absorplayabilmesinden bahsediyoruz, hem de belli bir band seviyesinde olmasından bahsediyoruz. Bunun üstesinden gelebilmek için, çünkü böyle bir katalizörü tasarlamak oldukça zor, iki farklı band aralığına sahip, aslında tek başına bu redox kapasitesini karşılayamayan band yapısına sahip olan iki farklı katalizörü heteroeklem yapıda sentezliyoruz. Heteroeklem katalizörlerin bize avantajı ne? Baktığımız zaman daha geniş bir redox aralığına sahip olmuş oluyoruz ve eğer kullandığımız katalizörler N tipi ve P tipi olarak ayrılıyorsa ve bunların Fermi seviyeleri buna göre bir uyum sağlıyorsa, dahili elektriksel alan oluşarak iki katalizörün arasında elektronların ve hollerin etkin ayrımı gerçekleşiyor ve etkin yük ayrımından dolayı katalitik aktivitenin arttığını görmekteyiz. Özellikle burada baktığımız zaman farklı heteroeklem yapıları görmekteyiz. A şeklinde baktığımız zaman Type 1 heteroeklem yapıyı görüyoruz. Bu aslında istemediğimiz bir heteroeklem yapı. Şundan dolayı Fermi seviyeleri birbirlerine yakın olduğu için iki katalizörün arasında elektriksel dahili alan oluşmadığından dolayı yüklerin etkin ayrımından söz edemiyoruz. Bizim en fazla tercih ettiğimiz B kısmındaki heteroeklem yapılar. Bunları da aslında Fermi seviyesine göre iki farklı katalizörün Z-şem veya S-şem olarak ayırabiliyoruz. İki mekanizmada fotokatalitik hidrojen üretiminde oldukça efektif olarak kullanılan ve şu anda aslında akademik çalışmaların bu doğrultuda olduğunu görüyoruz ve biz de aslında bu S-şem heteroeklem yapıların endüstriyel ölçüye taşınarak fotokatalitik hidrojen üretiminin endüstriyelleşmesi üzerine çalışmalar yürütüyoruz. Endüstriyel ölçüye baktığımız zaman ilk baştaki fotokatalitik hidrojen üretiminin lab ölçeğindekinden farklı bir durum görüyoruz. Burada seri bağlanmış bir reaktör silsilesi görmekteyiz. Buradaki parametreler aslında lab ölçeğinden daha farklı. Örneğin akışın burada daha önemli olduğunu söyleyebilirim. Çünkü daha büyük bir sistem olduğu için akışı iyi kontrol etmemiz gerekiyor. Burada baktığımız zaman bir ölçeklendirme de görüyoruz. Aynı şekilde bir reaksiyon tankı var. Pompa sistemleri vesaire bir komplike bir sistem var. Bunun içinde aslında bir kimya mühendisliği çalışmaları gerektiriyor. Biz laboratuvarda elde ettiğimiz STH verimlerini bu yüzden koruyamıyoruz. Çünkü bunun optimizasyonu baktığımız zaman başlı başına bir sistem. Ben bu konuda aslında doğrudan ben laboratuvar ölçeğinde katalizör tasarım gerçekleştiriyorum. Diğer arkadaşlarımız, firmamızda çalışanlar bu ölçeklendirme işini gerçekleştiriyorlar. Biz STH verimi %10 gibi elde ediyorsak laboratuvar ölçeğinde, bunu endüstriye taşıdığımız zaman oldukça büyük oranlarda düşüşlere sebep olabiliyor. Bu da aslında doğrudan doğal güneş ışığıyla çalışmanın etkisi ve sistemin optimizasyonunun gerçekleştirilmesi gerektiği bir kısımda bu çalışmaları yürütüyor. Burada biz solar simülatörler kullanıyoruz demiştim laboratuvar ölçeğinde. Eğer bunu doğal güneş ile yapıyorsak reaktörün üzerinde ışığın yoğunlaştırılması için kolektör tasarımı da gerçekleştiriyoruz. Burada baktığımız zaman kolektörler arasında parabolik kolektörler daha fazla tercih ediliyor. doğrudan fotokatalitik hidrojen üretimi için kullandığımız reaktörün üzerine güneş ışığını yoğunlaştırarak hidrojen üretiminin daha yüksek gerçekleşmesini, endüstriyel ölçekte lab ölçeğine daha yakın gerçekleşmesini sağlayabiliyoruz. Ölçeklendirmeden bahsetmiştim. Burada baktığımız zaman pilot ölçekte bir sistem görüyoruz. Bunu endüstriyelleşme konusuna taşıdığımız zaman dediğim gibi az önce bahsettiğim parametreler devreye giriyor. Yan tarafta da bir CFD çalışması görüyoruz. Katalizörlerin boyutuna göre, şekline göre akışın ve katalizörün akış içerisindeki dağılımının modellenmesi gerekiyor. Oluşabilecek problemleri görebilmek için. Biz sistemi tasarlarken bir yandan da CFD çalışmalarını yürütüyoruz ki sorunları en başından görebilelim. Fotokatalizörler için konuşuyorum. Baktığımız zaman Kazunari Domen ve arkadaşları bu dünyada aslında bu işi gerçekten yüksek STH oranlarını gerçekleştiren bir ekip. Tokyo Üniversitesi'nde çalışıyorlar. Burada baktığımız zaman panel tipi bir fotokatalitik reaktör görmekteyiz. Az önce akıştan bahsetmiştim. Partiküllerin işte kararsız hale geldiği ve türbülent akışın fazla olduğu durumlarda, akış hızının korunamadığı durumlarda farklı parametrelerin gerçekleştiğinden bahsetmiştim. Burada aslında katalizörleri immobilize edildiği ve ince tabak halinde bir panel reaktör tasarlandığını görmekteyiz. Ve STH verimi olarak da bu çok önemli. Yani lab ölçeğinde eğer bir sonraki slaytta onu söylüyorum. %5 STH'ın üzerinde bir pilot sisteminiz varsa bu sistemin endüstriyelleşebileceğini söyleyebiliriz. Yani ekonomik olarak hidrojen üretiminin gerçekleştirilebileceğini söyleyebiliyoruz. %5'in üzerinde ise ve 2018'de gerçekleştirmiş oldukları çalışmada %10 STH verimini yakaladılar. Ve aslında kararlılık da burada önemli ve kararlılığı da şu şekilde gerçekleşmiş. 150 saatin üzerinde herhangi bir kararsızlık meydana gelmiyor ve 1000 saate yakın bir sistem çalıştırıldığı zaman sadece %36 gibi bir katalitik aktivite düşüşü söz konusu. Bu da aslında şu ana kadar gerçekleştirilen çalışmalar arasında en yüksek verimler ve en yüksek kararlılık seviyeleri. Hangi katalizörle çalışılmış? Stronsiyum titanat, alüminyum katkılanmış stronsiyum titanat. Normalde stronsiyum titanat görünür ışığı absorblayamayan bir katalizör. Yani görünür ışık altında ışık absorpsiyonu yapıp foto uyarılmış yük üretemeyen bir katalizör. Çünkü bant aralığı 3.2 civarı. UV ışığa duyarlı. Peki alüminyum katkılandığı zaman ne oluyor? Bant aralığı belli bir miktar daraldığı için görünür ışığı absorblayabilir hale geliyor. Hem alüminyum katkılanmış stronsiyum titanatı çalışmışlar hem de aynı şekilde rodyum kromoksit gibi kokatalizörlerle katalitik aktivitenin iyileştirilmesini gerçekleştirmişler. Verim, reaktör dizaynı ve aslında doğrudan sistemin kendisinin dizaynı. Burada başlı başına unsurlar. Ben katalizörün tasarımını ve elektrokimyasal olarak kağıt üzerinde bu işi yapabildiğini tasarlıyorum. Sonrasında sentezini gerçekleştirerek arkadaşlara reaktör tasarımı için yani onlar reaktör tasarımını gerçekleştiriyorlar. Sonrasında tasarlanan katalizörler sentezlendiği zaman reaktör ortamında pilot sistemde deneniyor. Burada da aslında doğrudan güneş ışığından yenilenebilir bir enerji kaynağı olarak elektrolize alternatif hidrojen üretim yöntemi olarak fotokatalizi endüstriyel ölçekte kullanılabilirliğini aslında sağlamış oluyoruz. Çalışmalarımız bu yönde gidiyor. Baktığımız zaman Kazunari Domen ve arkadaşlarının gerçekleştirmiş olduğu çalışma çok değerli, evet. Ama 1000 saatin üzerinde bir hidrojen 1000 saatin üzerinde %36 gibi bir azalım aslında biraz sistem açısından sorun. Bundan dolayı çalışmaların hala devam ediyor olması ve farklı katalizörlerin tasarlanarak aynı şekilde farklı pilot sistemlerin de burada tasarımının daha önemli olduğunu görüyoruz. Bu çalışmaların da gerçekleştirerek fotokatalitik hidrojen üretiminin endüstriyelleşmesini öngörüyoruz yakın bir zaman içerisinde. Çünkü ilk çalışma 1972 yılında gerçekleştirildi ve yine aynı şekilde 2018 yılında oldukça önemli bir sonuç alındı. elektrolizi alternatif olarak yenilenebilir bir enerji kaynağı olarak fotokatalitik hidrojen üretimini görmekteyiz. Beni dinlediğiniz için teşekkür ederim. Tabii.
Thank you for your presentation. Before giving you your certificate, do we have any question about presentation, hocam?
A, B, C tipi heterojunction'lar gösterdiniz. Orada B tipinin daha uygun olmasının nedenini ben tam yakalayamadım.
İki farklı katalizör arasındaki Fermi seviyesi farkı elektron akışı için gerekli olan elektriksel dahili alanı oluşturuyor hocam iki farklı katalizör arasında. Bu da aslında yüklerin daha efektif bir şekilde ayrımını sağlıyor. Yani oluşan foto uyarılmış yüklerin birbirinden ayrılması ve rekombinasyon oranının azaltılmasını sağlıyor. Çünkü bir foto uyarım gerçekleştiği zaman elektron tekrar değerlik bandına...
O grafiğe dönebilirsek çok iyi, daha...
Evet.
Burada iki band aralığına da uygun fotonlar düşüyor sonuçta panelin üzerine,
evet.
değil mi?
Evet, evet.
A'da da
biz
B'de
eğer birisi p-type hocam, birisi n-type ise p-n heterojunction'sa Z-sham olarak isimlendiriyoruz. Eğer ikisi de n-type'sa burada aslında S-sham olarak isimlendiriyoruz ve bunların UPS ölçümleriyle ultraviyole fotoelektron spektroskopisi ölçümleriyle work function'ları ve Fermi seviyeleri belirleniyor. Ve bunlara göre aslında eğer katalizörün iki farklı katalizörün arasında belli bir seviyede bir fark varsa Fermi seviyesi, birisi daha negatif, birisi daha pozitif elektrokimyasal olarak iki katalizör arasında elektriksel dahili alan oluşuyor ve uyarılmış yükler burada bizim çalışmalarımız genellikle S-sham üzerinden yürüyor. Diğerlerinde aynı şeyden bahsedemiyoruz çok fazla. Yine aynı şekilde var. Ama genellikle kullandığımız Type 2 heteroeklem yapılar.
Teşekkürler.
Okay, thank you all, and thank you being here with us, with your support to our conference. This is from us certificate of appreciation. Sorry for English. And we made a donation in the name of yours to our scholarship foundation. And
teşekkürler.
Thank you. And we'll continue with our Okay, let me introduce you our next speaker. Okay, Soner Mülayim. Soner Mülayim received his BSc in Electrical and Electronics Engineering from Gazi University in 2016 and MSc in Electrical and Electronics Engineering from Zonguldak Bülent Ecevit University in 2020. He is currently pursuing a PhD in Electrical and Electronics Engineering at Gazi University, focusing on cybersecurity. Soner has worked as an R&D engineer at some technology since 2022, specializing in fiber optic sensing technologies, data analysis, and Python applications. He previously contributed to Aselsan's MIDAS project, focusing on distributed acoustic fiber optic sensors and system calibrations. His research interests include fiber optic systems, signal processing, and cybersecurity in engineering applications. Please welcome.
Thanks for introduction. Today, as some technology, we are
going to and who we are. But first of all, the fiber optic sensing systems are among the innovation pushing the boundaries of technology. As Max Planck once said, science advances by following the light that nature offers us. It is the key to understand our universe. So with following this guiding light as some technology, we developed and successfully deployed POTAS DAS system with utilizing a national resource around the world. I want to first introduce ourselves, who we are, and what we are doing. The some name derived from those four esteemed individuals. Some name is Sedat, Ayşe, Mustafa, and Murat. Also, I want to mention those four people are the technical people, which is Mustafa Akşit and Ayşe Akşit, graduate from Middle East Technical University in Physics department. And we founded in 2003, and now we are over 200 employees and 2 factories and over the 10,000 active products. And also those information is like in here, like we are CERN's trusted suppliers. And also the recent time we take running up awards from fiber optic associations about the seismic application of our DAS system POTAS. So this is actually our timeline of our history. We start in 2003, and we established our R&D center in 2018, and now we are in here with different prizes, different patent solutions, and different type of applications in fiber optic cables and fiber optic sensing solution areas. So we are not, our motto is we are not just a fiber optic cable manufacturer, also we are manufacturing endpoint solutions like the sensing systems, POTAS, and our recent project is completed the DTS, the distributed temperature sensing, and also another type of products like military tactical fiber optic cables. And this is our connectivity ecosystem. Our departments are telecom, IT, heating, and testing security solution group management. We are in here, and I am at the R&D department as an R&D engineer. In here, I want to especially mention in here because I'm in that department. We are always making a research with academy and development with our knowledge and our laboratory equipments. We have 2 facilities for now. I said for now because we are in the stage of producing the fiber optic cable core by ourselves in Turkey in the first time. Not a commercially in Turkey, already producing in Bilkent University in Unam, you already know, but
in commercially, we will the first company in Turkey that will produce the fiber optic core himself. And we have also two offices. One is at Germany and the other one is in at the Ankara. So let's start with the basic fundamentals, which is you already know, but I want to make refresh our knowledge with fiber optic technology and distributed sensing systems before we talk on photos. And this presentation will cover fiber optic cable structure, types of fibers, propagation mechanism, attenuation factors, and real-world photos applications. So basically, if you want to mention on the fiber principle of the fiber optics, it depends on the actually total internal reflection. The total internal reflection is just the showed in the image. It is the depends on the Snell's law actually. The differences between two medium creates a refractive index differences, and if this fiber laser goes through the fiber optic core, types of scattering in fiber optics. There are four scattering in fiber optic sensing actually, but mere scattering as we the known in literature currently and not using for a sensing solution, but Rayleigh and Raman Brillouin scatterings are used in different ways. For example, Rayleigh is occurs due to interaction with laser, I mean light with molecule in the core, and it creates an elastic scattering with effects of acoustic around fiber optic cables, or the seismic effects around fiber optic cable. And we are using in technology in dust systems the Rayleigh scattering, and the Raman scattering is inelastic scattering interaction between the light with molecular vibration, and Raman scattering creates two components. One is and show in here the anti-stock and stock signal. Anti-stock component is temperature related component, and stock component is actually used for a reference signal, and the DTS depends on making a ratio to these two signals to get the temperature information along the fiber optic cable with different locations. And Brillouin scattering is a scattering type make a frequency shift in the scattering signals. This scattering uses in DSS technology with for to sense strain or temperature, but most commonly strain application can handle it with using Brillouin scattering. And the brief look for the fiber optic cable structure. As we can see, there is a different layer in the fiber optic cables. And one is the core, cladding, coating, tight buffer, string members, and cable jack. Core is the medium that we use to transmit our signal in the fiber optic cable, and cladding is the medium that create refractive index differences to make sure the laser will be reflect in the core. and coating is for the some kind of protection like a moisture or the chemical effects, and it can be also called as a strength members, but the coating we can call it is it a tight buffer or bare fiber. It's kind of a coloring the fiber for the production. Like as I mentioned, there are different type of strength members like Kevlar or steel braiding or a different type of material for make sure the cable will resist factors such as moisture and chemicals. Actually, there are commercially two type of fiber optic cable, multi-mode and single mode cable. Multi-mode cable also two types with different core sizes, and single mode cable is a standard 9 micrometer diameter of the core. And if we compare those two type of the fiber optic cable, single mode cable has a loss differential losses and less attenuation because of the core size, and it is using most commonly a long distance transmitting and also long distance sensing solutions, for example DAS systems. But the multi-mode cables as a beneficial with larger core size, it gives us to inject high power lasers than single mode cable, but it is also another backwards like modal dispersions and chromatic dispersions, but it will be also in the same in single mode, but modal dispersions is a big challenge in multi-mode cable when we talk on the higher ranges like over the 15 kilometers. But under the 15 kilometers, like a DTS application, it's more beneficial using the multi-mode cable because it doesn't affect as much like the data transmitting. And about the light propagation and attenuation, the attenuation refers to gradual reduction in the intensity of light as it travels through the fiber optic cable. It is actually we can specifically mention with that with the scattering and absorption. Scattering is the light encountering microscopic irregularities in fiber core and creates some scatterings like Rayleigh or Brillouin or Raman. Absorption is the the name. It's some of certain materials absorb a smaller fraction of the light energy, and it's make the gradual reduction in the intensity per kilometer. And we mentioned this attenuation decibel per kilometer, and depends on factors such as wavelength of the light and type of fiber being used. For instance, attenuation is typically lower at a wavelength of 1550 nanometer due to minimal absorption and scattering in this range, making it ideal for long distance communication and also long distance sensing applications. And also another challenge in fiber optic sensing or fiber optic data transmitting is dispersions. Dispersions refers to spreading of light pulses as they travel through fiber, which can degrade signal quality and limit the transmission distance. There are two types of dispersions. One is chromatic dispersion, and the other one is modal dispersion. The modal dispersion actually in the multimode fiber optic issue, because of there's a different way of the in the fiber optic core, and it creates a different reach time in the every signal in the fiber optic core, and it creates overlap or signal mixing problems. But chromatic dispersion is in the every fiber optic type, single mode and multi-mode. It is the actually occurs because of the different wavelengths of light at different speeds through the fiber occurs this. In optical communication, data transmitting using light pulses of various wavelengths over long distance, these pulses spread out as like we see in here. Sorry. Like in here, the pulses that we injected in a fiber optic cable, and it's getting spread with distances. And to overcome this issue, using dispersion shifted fibers or dispersion compensating modules can be used to overcome this issue. Also, there are some type of fiber in ITU standards like G655 is a non-zero chromatic dispersion fiber optic cable type. And this is the modal dispersion that I mentioned. To overcome this issue, single mode cable, to use the single mode cable is a solution because it's just only mode for the transmitting. And just a brief information about DAS technology before POTAS. DAS system which used in POTAS use a phase-sensitive optical time domain reflectometry to detect acoustic events along the length of fiber optic cable. When the environment around the fiber changes due to vibrations or disturbances, it alters the phase of the backscattering light, which is detected by DAS system. So how it works? This is the actually the basic architecture of phase-sensitive OTDR systems in A. This system sent a pulse laser to sensing element, which is the fiber optic cable, and when the pulses goes through the fiber optic cable and interact with acoustic effects, it's shift the actually it's create differences in the backscattering signal, and with using a coherent detection method like balanced photodetectors or balanced photodetectors, we get the intensity differences like shown in the figure. And if we're gonna start to mention on POTAS system, POTAS is designed for distribute acoustic sensing over a fiber optic line up to 100 km. It can detect various activities such as walking, digging, climbing, car trespassing, or fence cutting activities, providing real-time detection and classification. And this is our devices. As you can see, there are two devices. this one is our interrogator, which consists data acquisition cards, electronic cards, and optical components. And this is the server that runs our user interface and AI. So if we want to talk on PHOTOS hardware structure, this is the basic architecture of our hardware and interrogator. As we can see, there is a laser, 1x2 splitter, 2x2 coupler, and EDFA, which means the erbium doped fiber amplifier, an acoustic modulator, a oscillator, and finally a balanced photodetector. The laser, which is ultra narrow for DAS systems, sending the continuous wave into the 1x2 splitter. We divide the laser, a continuous laser, by a ratio, and one is goes to the one path direct towards the erbium doped fiber amplifier, and the other one towards the 2x2 coupler as a reference. And the amplified laser by ETFA created a pulsed laser with acoustic modulator. Acoustic modulator is modulates the frequency and intensity of laser pulses by utilizing acoustic waves to alter the properties of light traveling through the fiber. These modulations allow us precise control of optical pulse timing and frequency shifts, which are critical for accurate detection and signal processing in DAS application. And the circulator directs the signal into the fiber that we call in fiber under test foot, and reroutes the Rayleigh backscattering toward the balanced photodetector, and 2x2 coupler is combines the reflected signal and the reference signal source, enabling further analyzing. And balanced photodetector components detect the weak signal, Rayleigh signal, and converts it into a radio frequency RF signal for our data acquisition parts. And about the system principle, PHOTOS detect acoustic signal occurring around the fiber optic cable via backscattering pulses. As I mentioned, we have different kind of classification, such as climbing, digging, passing car, and another type of classification. And threads can be detected in real time with high precision, long range fiber optic cable in areas such as campus or oil pipeline, highways, ports, and other places. The data structure, if you mention about data structure in the PHOTOS, PHOTOS system captures continuous acoustic signals along the fiber optic cable. These signals represent various disturbances such as walking, digging, or climbing. And about the format of the data, the structure format of data is efficient processing and analyzing, like time-stamped data, signal amplitude, and frequency information for each channel along the fiber. So what we are talking about is this one. I don't know, it can be seen, but this axis is meaning the range as a kilometer, and the vertical axis is meaning the amplitude of the backscattering signal. As you can see in here, this is the raw signal we get from the fiber optic cable. And also there is another visualization we call is waterfall, and this axis shows again the distance as a kilometer, and the vertical axis shows the time of the signal, and the heat of the colors means the amplitude of the backscattering signals. And the most important part actually to classify all of the signals is the AI side, and the POTAS utilize artificial intelligence AI for anomaly detection by incorporating machine learning algorithms. The system can classify disturbance based on acoustic signatures, and convolutional neural network CNNs are often employed for identifying and categorizing the type of disturbances, such as digging, walking, or vehicle movements. And about the training the models, we have a larger data set that include labeled acoustic signals. This ensures that the system can accurately distinguish between harmless background noise and genuine traits, and real-time classification. Once trained, the AI model operates in real-time, enhancing system ability to quick and accurate identify potential security threats. And conventional neural network and training the validation is about CNN used to process the acoustic data captured by DAS system. These models specialize in recognizing the pattern in the data, and training and validation. Actually, the CNN model is trained using labeled datasets that include different types of disturbances, and the training process involves multiple epochs to ensure the model learns the distinguishing features of each disturbance type. And how we evaluate the trained models. The evaluation metrics are for us accuracy, precision, recall, and F1 scores. These metrics helps fine-tune the model to minimize false positives and maximize the detection algorithms, the detection accuracy actually. Currently, we have 5 models with single channel and dual channel. The current are completed, and the commercial version has longest distance is the D50 model, which is means 100 kilometer sensing range in a single line. But under development, we have another type of model with 140 kilometer sensing range. The general features, if we look quickly, buried on fans or hybrid solution, class 1 laser not producing damaging radiation levels, can use previously deployed fiber optic cable. This is the most important part, because in pipeline applications, most commonly it's already buried cable. It is called a brown field, and the green field is meaning there is no pipeline already buried, and it will be get digged and open a trench with pipeline and fiber optic cable. It is called greenfield, but most commonly projects that we see is brownfield, which is already buried fiber optic cable. So our customers and the most of the projects asked for can we use our fiber optic cable is already deployed, and we can say yes, we can use it. It is not a specifically fiber optic cable we need for the system, but in the fence application we are gonna give some advices for increasing the sensing methods like installation fiber optic cables. Also, we have our own user interface that I will be mentioned, and as I mentioned first of my speech, every component like the software and the fiber optic components and the electronic cards are developed in our national resources and in our R&D center. About the general features, those are the threads, and the metrics for the threads is distance from the fibre. We can this is means we can sense a manual digging far away from the 5 meter, or we can say we can sense a human that try to how can I say, a person try to get enter the facility without access or without a permission. We can sense him by a 4 meter distance, and also it creates an alarm on UI with a human walking, and the system also has a 10 meter accuracy. This means the system has a 10 meter spatial resolution, and that means for a 100 kilometer application we have nearly over 10,000 points, like 10,000 microphone and listening to all the line. The user interface that I mentioned are developed by our engineers, and currently always it's developing because of we are getting demands on the field from the customers, and we always increasing and enhancing this UI with demands of the customers. So we have a geographic information system. It shows the violation that occurred on the fiber with a latitude and longitude, and also user can make a acknowledge and export for a report, and also it can trigger a integrated CCTV or another type of third-party systems, like for example the horns for the military security, or like a drone integration. Also, the user can define zones, and it can be muted, or it can be give another color or another type of name. So about the application in PHOTAS, the first of my beginning of my speech, I mentioned we get an reward from Fiber Optic Association, a runner-up reward. It was about this project, active seismic acquisition, As all of us know, there is a possible earthquake in Istanbul, the fault line under the Marmara Sea, along which a fiber line established is monitoring by POTAS in now currently, even in the even the at the nights or the days, we always observing and getting the signal with POTAS, and it's also creates and alarms with earthquake detection, like for this stage, but with Kandilli and the Istanbul Metropolitan Municipality, we are aiming to make a system that can sense and predict the earthquake with P and S waves in the earthquake. So it will be a protection before the earthquake, like cutting the all the electricity and gas in the city, or stop the trains already in the way. And another type of application is third-party intrusion. We made this test and the project with our country's petroleum company, Potash. Multiple POTAS units have been successfully commissioned at the actual site with an architecture that if one DAS unit fails, the rest of units shall not be affected. This project was really challenging one. If I don't wrongly remember, our friends at the field sometimes hit the ground with pickaxe over 160 times to get the data for manual digging, and we get over 1,000 labeled data for just this project, trained our AI. And upon our successful work together, signed a partnership agreement with some technology, POTAS. And another type of TPI project with Mexico petroleum company, Petróleos Mexicanos. POTAS has been installed in Mexico, and acceptance test has been successfully in progress and finished. We also successfully finished project in Pemex for a TPI application. And another type of application in DAS system, actually the POTAS, the intrusion detection, perimeter security. We have several type of fields that we already installed and we already finished projects, like a Mexican Ministry of Interior, Durango Prison, Michoacan Prison in Mexico, Optocon Data Center, Jihlava, Czech Republic, Çamlıca TV Tower in Istanbul. It is like, as you can see, the fences protected with POTAS, and Türkiye Bilişim Vadisi, Teknopark Bursa, and Swiss Hotel Bursa has our system for perimeter security. Also an iron and steel plant in Turkey, Malaysia, natural gas facility in Turkey, Australia, a solar farm in Brazil, and also a military base perimeter security in Europe, and a nuclear plant perimeter security in USA. Also, POTAS enables telecommunication companies to monitor their security of data network infrastructure at sea and land in real time and complete manner at the physical layer, and gain necessary time for responses. And this is our map, world map that we already installed and our finished project on the world. And I want to also mention our latest project, and this project also actually was a TADEP, TÜBİTAK TADEP project, and we successfully finished it. And we are now in certification stage with a European norm, EN 54. This norm is as a requirements for fire detection projects. So how DTS work? I actually mentioned a little bit in my speech, beginning in my speech. We using Raman scattering in DTS technology. Temperature sensing DTS system operates a short pulse of light, typically a laser through an optical fiber. As light travels through the fiber optic cable, it interacts with molecular vibration, which is affected by temperature, and it creates two components: stock component and anti-stock component. Anti-stock component is anti-stock component actually is temperature related, called as temperature related component, which is a higher wavelength, in other way, higher frequency, and actually lower wavelength and higher frequency. Stock components are lower frequency and higher wavelengths components. With using those two frequency wavelengths, backscattering wavelength, we creating a temperature information on the fiber optic line, along the fiber optic line. And about the application for DTS, like as I mentioned, fire detection in tunnels. Most commonly, the highway tunnels is the projects in the fire detection, but subway stations or rooftop solar panel farms on the facilities are really required for fire detection, because the fire and temperature rapidly increases and leads catastrophic fires. And about industrial monitoring, and industrial settings like a conveyors or another type of like a pipeline with some kind of chemical material transmission, there is a consist with observe the temperature of the material inside of the pipeline. So it will be need to use a DTS to observe the temperature of the pipeline. And environmental monitoring, it can be used in ecological damage or pollution in lakes or rivers. It will be help detect the contamination or pollution. By the pipeline monitoring, it's another type of high demand application in DTS projects to make pipeline integrity monitoring, where the system detect the temperature fluctuations that may indicate a leak or structural failure. Because in pipelines, some of the liquids are getting heated for the transmitting, and this heat process need to be handled carefully, because like sulfur oxide liquid silver oxide has a range of a temperature, and it should be in the range of that temperature. So a temperature observing is really crucial in that applications. And this is our BTS device. It's for now it has 4 different type of model with different ranges: 2 kilometer, 4 kilometer, 8 and 10 kilometer. As you can see, there is a 4 optical channel and 48 relays with NC or NO relay, and it is a 0.1 Celsius temperature resolution and 1 meter spatial resolution. And about conclusion and future vision, as we look ahead, the integration of advanced fiber optic sensing technologies will become cornerstone in the future of smart infrastructure, with ongoing developments in LF-DAS, low frequency DAS, and the DTGS, distributed temperature gradient sensing. We expect to see a broader application in industries such as energy and environmental protection and security. Our goal is to continue enhancing these systems and ensuring more reliable, efficient, and intelligent monitoring solutions that contribute to safer and smarter infrastructure worldwide. And as the summary, throughout this presentation, we have explored application of fiber optic sensing technologies, particularly DAS and DTS, and real-time infrastructure monitoring. These technologies provide enhanced security leak detection and environmental monitoring, improving the safety and efficiency of critical infrastructures. I want to thank you for your attention. With you further in discussion about fiber optics sensing and its future application, please feel free to reach out with any question and for future collaborations. Thank you.
I thank you too. Do we have any questions about? Okay. Marco.
You said that sometimes customers ask to use their already cables which are already in the ground for your DAS systems.
Yeah.
But you have an AI trained on, I guess, on your cable, right? So how do you retrain the model, or what do you do to enable your AI to detect in their type of cable, which might have already some defects or something?
Actually, if the cable is already buried one, the cable type probably is G652D, and we have our testing field with a buried and a fence application. And as the good part of manufacturing fiber optic cable, we have different type of fiber cable. So we get different type of model data for every type of fiber optic cable. Yeah, actually.
Okay.
Yeah.
Nice.
But it's most commonly is about G652 type of fiber, because it's the most commonly used commercial fiber optic data cable in the pipelines. But some of pipeline companies like Potash or another companies use G655. and also we have that fiber optic cable with collecting data. But this system is not like a plug and play. It needs some time to make the calibration. While we're doing, we get the data with different fields, like as I showed in the world map. We get different type of soils with signals, and this really increased our AI sensing capability, because every field means a different type of data, and it's really makes our systems stronger than before. You're welcome. Yes,
I have two questions concerning the photo system. One is, has it a built-in memory, and if yes, how big? And the second question is, you said you first split and then modulate. Wouldn't it be better to first modulate and then split?
Well, actually, in homodyne and coherent sensing, there are sensing arm and reference arm, and in sensing arm we use modulated because it is not like not like a OPDR frequency frequency reflectometer. We use the pulsed laser because we trying to make it as a how can I say like a radar type of technology to make the system with get the time knowledge with flight time of the light. If we I don't know make the split make the modulation before split, it will not be beneficial, I believe. About actually, I'm not sure it will be the answer that you seek for, but about the memory, I couldn't understand. Could you please repeat your question about memory?
How big is it? How long can this device, the unit store, for how long does it?
The stored logs of the events? Yeah, actually it depends on the customer need, because we are using server with AI server with SSD rates. So basically we have 1 terabyte storage, but it can be increased with demand of the customer.
Thank you for the presentation. In your while training your AI, you said you are measuring accuracy, precision, F1 score. What about these numbers? I mean, do you have any rule of thumb? Do you have a limit that you say, if this is some percentage, we are done with that model? Do you have any rule of thumb for that?
Yeah, actually the confusion, actually the metric, our AI engineer looking for the value that he, as you mentioned, the limit, it is good enough for us with the confusion matrix, and the F1 score, he looked for it, but the number, it should be asked for him, because I'm the Photonics side in the project, and he is the AI side in the project.
Okay, many thanks. When you are working with already installed fibers, is it dark fiber? If not, does your sensing activity influence the already running telecommunication signal?
Excuse me?
When you are you have a contract with already installed fiber, are you using dark fiber, or if not, does the sensing activity influence the already running telecommunication signal in that fiber?
Actually, it is not affect the communication in already installed fiber, because we are how can I say, the fiber optic cable has a different cores in the cable inside. In the pipeline, if I don't remember wrong, 24 cores inside the cable, and we just need one core, dedicated core for it. So we just use that core for our application.
Okay, it's dark fiber.
Yeah.
I couldn't understand the difference between the DTS and DTGS.
Yeah, it is actually a new hot topic in DAS system. It is meaning the distributed temperature grading sensing based on low frequency DAS actually. It works like, for briefly explanation, in DAS systems, the frequency under the 10 Hz, the backscattering signals, consists strain and temperature effects in DAS. But over the 10 Hz, the acoustic effects will be more powerful to make not understandable to temperature effects. So maybe you wondering in DAS how the temperature effects can make an effect in the signal. It actually depends on the refractive index differences in 2 points. Like we imagine like this. There is a 2 point in fiber optic cable, and when a temperature affects the fiber optic cable with using low frequency DAS, there is a refractive index differences occurs between 2 points with resolution, spatial resolution in the system, and these 2 points create with different refractive index in these 2 points creates a wavelength with the wavelength creates a phase differences between 2 points, and under 10 Hz it can be sensed with this effect, and therefore it will be reverse working principle with DAS, because in DAS systems we use and in literature uses some filters like high pass filters that use above some of the signals in a frequency, but this DTGS uses like a low pass filter that doesn't care about the over 10 Hz components in the frequency information.
Okay, okay, thank you. Then DTGS is not based on Raman.
Yeah,
It's Rayleigh.
Yeah.
Okay, okay, thank you.
That's right.
I think our questions are over, and then let me give you our certificate of appreciation for participating in our conference. But before, we need a background. Yeah, this is our background. Okay, this is for we made a donation to our scholarship foundation in the name of yours, in behalf of you, and I want to give this to you too. Okay. Welcome again. After our short break, our next speaker is Alper Ülkü. Let me introduce him to you first. Alper Ülkü received his BSc in Electrical Engineering from Middle East Technical University and MSc in Electrical Engineering from Gazi University in 1991 and 1999. Currently, he is a PhD candidate in Material Science and Engineering at Gebze Technical University and works as a team leader, chief engineer of display technology in Aselsan Microelectronics Guidance and Electro-Optics Business Sector, Turkey. His research interests include thin film transistors, display materials, display optics, radiometry and photometry, display ruggedization process, and AMOLED device fabrication. He occasionally lectures on the technical elective course Optical Display Technology and Design course in Ankara and Karadeniz Technical Universities. This is him with short words, and let's welcome him here for his speech. Named Leakage Current Reduction by the Electric Permittivity Graded Stacked Gate Oxides for FinFETs. Thank you.
Thank you very much. Ha, tamam. Hı hı, tamam. Hı. Nasıl göreceğiz? Ha. Hı. İyi akşamlar. Good afternoon. My name is Alper Ülkü. I'm from Aselsan. This is the largest defense electronics company in Turkey. We have been working in OLED technology and thin film transistors since the start of 2010s, and I'd like to introduce you today a topic on leakage current reduction for thin film transistors, namely the tri-gate FinFETs. Actually, I'd like to thank Canan Varlıklı, Professor Canan Varlıklı, for inviting me. Thank you very much. And I'm honored to be here for the wonderful photonics event. And I also thank you, all the students and staff that help us. Thank you very much. So I'll try to brief you on this designing thin film transistors. It's obviously a small step for the rest of the world, but it's a big step for Turkish display community and industry. And because if we make it, we will be solving the problem once for all. And through this endeavor, a long road of TFT business and array design, I'll try to share what we have, explored some alternative paths on design of these. I worked under the guidance of Professor Ahmet Yavuz Oral in Gebze Technical University, and my thesis is about thin film transistors, performance and application to the OLEDs. We have a small but effective technology team at Aselsan. At my company, it's deeply on aviation electronics. We started with designing the displays, and then we started designing the LCD ruggedization process, and then we passed our way to OLED technology, so that we are trying now the deepest components within that technology, so that we try to optimize their performances right now. Today I'll try to brief you on FinFETs and their importance in modern electronics, what we have in dielectric technology in FinFETs, the functionally graded materials, that is the main topic here, functionally graded dielectrics, namely, and our research problem. And we have a simulation tool called Silvaco Atlas, TCAT. So we try to minimize our effort with starting some simulations and running many of them before we optimize our devices. And then the model parameters, performance metrics, we will be talking about, and results, of course, and some insights will be presented. Let's start with the typical diagram, Moore's law. This law states the number of transistors on the microchips will double every 2 years, and this law still prevails. As the law has not been violated since 1970s, we constantly observe that the semiconductor companies are exploring ways to increase the transistor density per millimeter square. And when we see these transistor counts, nowadays this density lies in the borders of 200 million transistors per millimeter square, which is the 1 millimeter square is the tip of my pen. So this is an incredible amount just today, but what happens tomorrow, of course, we'll see. Starting from 2013, chips have been fabricated employing this FinFET technology. Well, as you have guessed, it means a lot in terms of application of all walks of life of biotech, nanotechnology, and artificial intelligence. So FinFETs are all around, and starting from the planar transistors, now it's FinFET time, and now next generation will be the GAA FETs and the 3-dimensional FETs. We will see some examples on them. This is the NVIDIA chip, and this chip has it has 76 billion transistors in 600 millimeter square area. So the density is 125 million transistors per millimeter square. So that's a really huge amount. How do they achieving this? Well, this is the device. FinFET is the device. We see here the 14 nanometer case, but the deepest one is the now 3 nanometer. 3 nanometer technology is the latest technology, and TSMC's TMSC is Taiwan Semiconductor, which is the leading company, or Intel. They are working on the 2 nanometer technology, and they say that they will be reaching the 20 angstrom technology in some 2-3 years. Well, this is really getting in hurdles. So now you are looking at the mentioned FinFET. The thin-field effect transistors are actually a type of non-planar or 3D transistor that came out of the need to overcome the limitations of traditional MOSFET designs. What do we have here? I mean, what is the benefit of FinFET? For example, the most effective thing here is the 3 phases. Not only in planar transistor, we have only one side and surface charges, but here we have 3 sides of surface charges. So the area and the area of the surface charges tripled. So we have a serious advantage. Name FinFET comes from the thin conductive layer that protrudes from the surface of the device that resembles a fish's fin. This additional surface area allows better control over the current flow, leading to improved device performance. It consists of the metal gate deposited on top of gate dielectric, which is sandwiched between highly doped N-channel silicon and the gate metal. Insulator we also call as the buried oxide, the box. Being a three-terminal device, FinFET source and drain connections are to be made on these thin walls via lithographic processes. The orange section is the gate dielectric our work is concentrated on. Just this dielectric that runs through the channel and sandwich between gate and the channel. So we have maximum charge control with not one, but two, but three phases of gate metal. Thus, efficiency of the area is improved significantly. And we have a stronger depletion region, and that better inhibits the leakage current and superior channel performance. This advantage has been adopted since 2013. So it has been in the area, in the chip technology since maybe 11 years. And they announced that, as I told you, the TSMC announces that already announced the end of FinFET era. What happens to FinFET now? It's getting obsolete. How? This is how. Planar FETs have been in the market for maybe 80 years, maybe more than 80 years. And now, last 20 years passed with FinFET, and it happens now the GA FET came to 10 years ago, it was invented. And we see the nanowires, not the three faces, but the all four faces of the semiconductor channel is facing the gate through the dielectric. And there's the nanosheet case also. So Samsung will commence high volume production of 3 nanometer GAA chips very soon. And Intel too plans starts its GAA implementation before TSMC. So, but where did all this begin? When we searched for all the transistors, this is from our review paper. In the beginning of 20th century, only until we gradually observed 6 stages of thin film transistor development. Here we expose some figures from our review paper. These phases of development starts with bulk planar architecture, which is the classical MOSFET. Addition of the buried oxide and the high K dielectrics. And after that, within 15 years of development, scientists paved the way to FinFET here. And it is fully commercialized in 2013. And this is what is happening now. Why? Because finally, what we see in color is what is happening in the fabs right now. Instead of using 90-degree fins, more than 70-degree inclined fins are used to ease the deposition of dielectric material evenly on the silicon channel. And now we are looking one of the masterpieces of fabrication called GA FET, gate all-around FET. You can observe that the drain and source metals evolved as a wall of conductors. Cyan-colored spacers are the dielectrics. And when you look in the BB cross-section, you can see the source drain channel as an oval structure. They are now trying to solve the parasitic effects that appear when these 3 transistors, instead of 1, are put on top of each other with the same conformal gate. This is another what Samsung is trying to produce right now. It's called the multi-nanosheet field effect transistor. On top of these, as we conducted a performance-wise review, the latest literature comprised of more than 70 papers within the last 3 years. We observed that the FinFETs with dual and triple heterogate structures and trigate FinFETs achieved the best performance, and trigate being the rock star holding the stage today. Our performance metrics were the subthreshold slope, the drain-induced barrier lowering, and ion-IF ratio is what we seek primarily in evaluating TFT performance. Double heterogate FinFET and triple heterogate FinFETs are the best performing ones. So let me explain you these performance parameters. Let's consume some time on this slide, as these are the most important figures of merit for TFT evaluation. The first one is the drain-induced barrier lowering. Every transistor has a threshold voltage as seen in the figure. This threshold voltage is the voltage where transistor switches its regime to pass a significantly high drain current. And when we change the structure of the transistor by design, say when add a different dielectric or change the channel width or change the channel length, this threshold voltage naturally changes. And once we set our transistor running, we do not expect that this threshold voltage will change, but surprisingly, it does if you change its operation voltage like the VDD, the drain voltage bias. When the supply voltage ranges from some millivolts to some volts, its VTH, the threshold voltage, might also change slightly. So we call this effect the drain-induced barrier lowering. So it's the delta of change in threshold voltage divided by the drain source voltage, or the drain voltage, let's say. I mean, the drain bias. And the second one, the subthreshold slope. So we need the double DIBL, let's say. It has to be minimized. I mean, our transistor will not be a good one if we have a high double. The drain-induced barrier lowering has to be a low quantity. And subthreshold slope needs also be smaller one. It's also the reciprocal of the transconductance, but here we take the natural logarithm of the drain current so that the unit SS becomes millivolt per decade. When you are using silicon as a channel, the subthreshold slope is minimum 60 millivolt per decade. If you change your channel material, SS can be decreased to lower values. And the final one is here is the ion-IF ratio. It's the on current of the transistor divided by the off current of the transistor, which is a nice figure of merit. If you have done a good job in designing your transistor, this has to be a high value. At least this value should be 10 to the power 5 in order to accept this device as a transistor. So that these are the fundamental performance metrics that we are in search of and for the performance. I have some words about gate dielectrics, of course, in FinFETs. Companies have been utilizing many types of gate dielectrics. You may see them in this slide. Their kappa, namely the dielectric constant, vary from 3.9 to 80, 95 in this case. And these are ranging from silicon dioxide to titanium dioxide in our case. And their band gaps also range from 3.5 electron volts to 9 electron volts. In order to isolate the gate metal from the proper dielectric field to control the drain current, gate dielectrics are of great importance.
So functionally graded materials are actually a derivative of composite materials, where certain material property within its geometry is not evenly distributed. Rather, it changes with the thickness of X or Y or Z axis. Here we have a stepped graded profile, for example, for dielectric permittivity. Here we have a smoother profile for any kind of material property. For example, this material property can be composition gradient, orientation gradient, fraction gradient, permittivity, and other material properties. So FGMs are, in principle, they are composite materials, but they are graded in some sense. So we may also have different phases of materials, of course, neighboring each other, so that as thicknesses varied, the material property changes from phase A to phase B. If we have a two material, it will be a single FGM, we say that. But if we have a double FGM, like this, we have three separate materials. So it starts with A, material A, then passes to C, and then passes to B. So as thickness changes, we have a double FGM with different properties. For example, we see here a metal to ceramic FGM, which the porosity changes as we travel from north to north inside the material. As we go from south to north, the porosity changes. Metallic phase, transition, ceramic phase. So this is a very nice example of FGM. Also, there are bark of a tree, human nail, human teeth are natural FGM materials. Human, some also natural, some bark leaves in the nature. There are FGM examples. And when we introduce the Greek letter epsilon to the FGM, it means that this material property is changing with a certain rule or formula. Either this independent variable is the thickness or powder density or some other property. In this example, the EFGM, the effective permittivity of the material, will vary according to a two-dimensional parameter powder weight density, and it's formalized with the Maxwell-Garnett distribution equation. So now our dielectric constant changes with the powder weight throughout the material. And now our research question comes here. Can we enhance gate dielectric performance via the functionally graded materials? The research on the stacked gate dielectrics on thin film transistors first appeared in 1994 by Kuo, when silicium nitride laminates with different dielectric deposition conditions were experimented and compared with single silicium nitride as the gate dielectric. This paper analyzed how the TFT mobility, threshold voltage, subthreshold slope, and ion and IF values was affected due to different gas flow concentrations. They only changed the gas flow concentrations, not everything else, but just the gas flow in the PCVD process. So when the PCVD process was changed, device channel became a different one, and we changed its subthreshold slope, for example, changed with the graded material. To analyze this in a better manner, we have been employing the Athena and Atlas TCAD software by Silvaco. Athena is the definition of the material structure, is for definition of the material structure. We define first our material structure in antenna and process engineering, and then we introduce Atlas. This introduces the electrical excitation to the defined structure and the electrical characterization. And of course, we have many other tools in Silico, but that's beyond our scope right now. This is our TFT model. Here we can see our modeled FinFET to be simulated with different materials. Actually, this is a 14 nanometer technology, meaning that the channel length is 14 nanometer. It includes buried oxide layer of hafnium dioxide. And in case it's alumina in the red area, hafnium dioxide in the middle, and titanium dioxide in the magenta area. And outside, we have the metal of chrome aluminum. So this is the greatest structure of our FinFET right now to be simulated. So other properties of the FinFET are as follows. I won't be reading all of them, but the gate thickness is 1 nanometer. Typical gate channel concentration is 5 to the power of 19 centimeters per square cube. Gate metal is chrome aluminum, and the total device length is 34 nanometers. So what are our dielectric materials here? Dielectric materials are, first of all, we have single material gate oxides for our control group. These are silicium dioxide, silicium nitride, alumina, hafnium dioxide, lanthanum dioxide, and titanium dioxide. These are designated at S1 as S1, S2, A, H, L, T. This is just for reading the graphics easily and generating the other dual material and triple material references easily. For example, when we have a double material graded gate oxide, for example, consisting of silicon nitride and alumina, we call this S2A. For example, for hafnium dioxide and lanthanum trioxide, we call this HL. This is just for this paper's scope. So the other ones are triple materials, and we call them by some reference designators. For example, the hafnium dioxide, lanthanum trioxide, and titanium dioxide triple material is called as HLT. And what about the thicknesses? The original thickness of the single layer was 3 nanometer in all cases, and double materials thicknesses are divided by 2, 1.5, 1.5, 1.5 everywhere. So double materials have just divide themselves, share the length of 3 nanometers between them, 1.5 nanometers for each. And we try to calculate the kappa, the dielectric permittivity of the sandwiched nano layer. Even we have to know that this effective dielectric permittivity is not the same as bulk permittivity. So we have to have a method for calculating this. And this method comes as in the next slide. So our stack structure is such. We have a silicon as a channel, the N+ channel. The dielectric permittivity of the silicon N channel is 11.7. Alumina 9. Hafnium dioxide 25. Titanium dioxide 95. And metal, we can accept sometimes metal dielectric permittivity as infinity, but generally it's not infinity, of course, because it has a limited length. If it is a bulk metal, we can accept as infinity, but generally you cannot accept that infinity, but it is big enough, let's say. And in the stack structure, when we try to have this structure in a nanometer scale, we have to change the dielectric permittivity value and calculate this value from the PEN model. We have a PEN model to calculate the kappa for each nanolaminate. Here's the formula. And this formula has been generalized in some papers so that we have the generalized version. And for example, you can see here the nanolaminate thickness versus the effective dielectric constant. Normally, titanium dioxide has a bulk dielectric permittivity of 95, but it all of a sudden, when it reaches to, for example, 10 nanometers, it decreases. It starts to decrease, and very drastically. For example, when we have a 1 nanometer titanium dioxide, all of a sudden its permittivity becomes 35-40, not 95. Okay, so we have to take this into account. And also, when we have multiple laminates, we have to take the Maxwell-Garnett model into account. So instead of having the series model, we use the Maxwell-Garnett model to calculate the kappa of the whole gate oxide. So this is the formula here. For example, if you have two materials, the A and B, this is the effective kappa of the two material case with the volumetric fractions. And the next one is the three material case. When we have a A, B, C material, the effective kappa of them, this is this formula we derived in this study. So, and after that, we of course have to have the performance metrics. Some of them I mentioned to you in the beginning. What do we have? I only didn't mention about the on-state gate leakage current. This is also a very important performance metric. It leaks from gate metal through the dielectric into the channel. So this is the reason why chips get heated, overheated. So a designer has to, if he's a chip designer, he has to minimize the gate leakage current. It's a very important factor. Off current and the leakage current are two important performance parameters for our metrics and FinFET. So in our study, we have run 41 simulations with all these 2, 3, and single layer dielectrics on top of each other as nanolaminates. They're functionally graded. Their permittivity is like a step. And these are simulated, and we have some very interesting results here. First of all, when our figure of merit is the drain-induced barrier lowering, our best, and also the ion-IF ratio, our best transistor consists of the silicon nitride plus titanium dioxide dielectric. They are both 1.5 and 1.5 nanometers thickness. This is the case. And if our this has an effective kappa of 24.26, 24, let's say. And the most, let me see, okay. One of the perfect transistors with the lowest IOF ratio is the alumina plus titanium dioxide one. And the other next perfect transistor is with the least gate oxide leakage current. This is the alumina, hafnium dioxide and lanthanum trioxide triple graded dielectric. This is the case where the minimum gate leakage current occurs. So this shows us that none of the single layer dielectrics are performing better of these lists. There is at least one graded dielectric that is much better than single layer dielectrics. So what happens then? What is the explanation for that? Functional gradation allows seamless transition between different material properties, reducing likelihood of failure due to abrupt changes in material characteristics. Thus, interface problems might be mitigated with FGMs. In the context of semiconductor devices, epsilon FGMs or kappa FGMs, let's say, can enhance the device performance by optimizing charge distribution, reducing leakage currents, and managing short channel effects more effectively. Here are some insights and some results which are visual. The minimum IOF happens in our GK FinFET at here. This is the minimized AT alumina plus titanium dioxide, and this is the zoomed version here. This is 6.45 10 to the minus 15 amperes, and we can safely conclude that titanium dioxide matched perfectly with the metal side better than the others. Why? Its bulk permittivity is very near to metallic permittivity. And the alumina and silicium nitride matched not so perfectly, but better than silicon dioxide and hafnium dioxide. Why? The lattices matched more perfectly. With the silicium channel, when the FinFET was in depletion mode. But when the FinFET is in accumulation mode, just the opposite happens. So in ion, let me see. Okay. So just the opposite happens in the ion case. The ion maximum ion current happens in the FinFETs like silicium oxide, alumina, and lanthanum trioxide case. So they have silicium dioxide in common. So we may also conclude that silicium oxide dioxide matched perfectly with the silicium channel as we know it. It matches perfectly with the silicium channel. I mean, it is very much commonly used dielectric material, silicium dioxide. It matches perfectly. But just in the on case, not in the off case. So this is a fact. And better than silicium nitride and alumina and titanium dioxide, the metal side has to be matched with hafnium dioxide and lanthanum trioxide as a rule of thumb. Why? Because their dielectric permittivities are higher than silicium dioxide in the on case. So we have some insights for you in this paper. So no, we have not detected any linear or quadratic relationships between gate oxide kappa and the other figure of merits. We don't have any linear or quadratic relation, but the best IOF performance have titanium dioxide laminate. That was my chance, but that is only my case. Well, as a recommendation, in Turkish defense sector, let's say, we have been into some deep designs, VLSI chips, thin film transistors, and some cases that are seemingly top-notch or better detail, let's say, for an electrical engineer and for material science engineers. The practical use of this case is not enough. You have to dig into that by searching for degrees, I think, because if I was not a PhD student, I would never reach such an endeavor. That's why I together with industry, all our students has to be allowed for their PhDs. some industries don't allow PhDs, but that's not a good case. So I thank to Aselsan for allowing me to make a PhD. So that is my case, and another general recommendation might be going very deep with the university. I mean, with ties with the university is very crucial. Your professor, you have to be tied with him in a better sense when you enhance, because you need him always. You always need him, because I mean, he will be providing insight what to enhance better in your design. I mean, in a company, you become a conformist with your design, working design. You have a working design. I mean, it works. But when do you enhance that? How do you enhance that? Somebody should be giving some insights to the end. That should be our professors and our pioneers in this. So getting ties is crucial.
Thank you.
Thank you for the question. I think, okay. Hi,
Sorry.
I have a question.
Yeah, sorry, it's back to a more technical question maybe. I was wondering, you have like 3 nanometer and you put 2 materials there. So you just have actually tens of layers of atomic layers there. But your formula doesn't contain anywhere, let's say, atomic mismatch, the mismatch between the bases of the unit cells. Does it matter to your opinion or not, or in the future, let's say?
Yeah, I mean, we are at the verge of producing this, fabricating. This is a perfect question. We have to see the effects, real effects. In ALD, an atomic layer deposition, we will be depositing this material in ALD, and our materials just come. I mean, we'll be starting experiments next week. So this has to be seen by us. We have to, first don't start. We have the modest 4-micron technology in Aselsan for most of our designs. I mean, this is a 10,000 more, 10,000 scale more. And why? Because it is the state of the art. This is the state of the art. I mean, we have to know after our chances of fabrication and characterization is done. Next year, I will be coming with such results, I guess. Thank you. Thank you.
I guess we have no questions. And thank you again for your nice presentation. I want to present it to you, but notice. Yeah, we need a background.
Yeah, of course.
Yeah, this is for your participation in our event. Thank you very much. Okay, and we made a donation on behalf of you for our students, and I want to present it. Thank you very much.
Teşekkür ederim.